applications. Today's session is focused towards quantum computing and how we can simulate quantum computing using Qiskit. The first part of the session is on variational algorithm, harnessing the power of a few qubits by Ritojit Majumdar. Ritojit Majumdar is a research scholar at the Indian Statistical Institute, Kolkata. He received his master's degree in computer science and engineering from the University of Calcutta and is a gold medalist from the same. He was an assistant professor at the Department of Computer Science and Engineering, BP Poddar Institute of Management and Technology, for 2 years prior to joining the Indian Statistical Institute. Ritojit was awarded the prestigious DST Inspires Fellowship from the Government of India for being the university topper. He is also the recipient of the Junior Research Fellowship from the Indian Statistical Institute from the year 2018. Ritojit has published more than 10 research papers in the field of computer science in various reputed journals and international conferences. His current research interests includes near-term quantum algorithms, quantum error correction, and the application of machine learning techniques in quantum computation. I request Ritojit to begin his talk. Ritojit, please take the stage.
Yeah. So is it visible?
It's coming up.
Okay.
Yeah, it's visible now.
Okay. So thank you. Let me first thank the organizers for inviting me here to give this presentation. Let me first thank the Government College of Engineering and Ceramic Technology. And I am just a student actually. So all those introductions, let's not fool you with that. I'm just a student who is trying to learn this quantum computing. I find it very exciting, very informative, and it's awesome field for me. So I'm just trying to learn, and today I'll be sharing with you whatever little I have studied and whatever little I have learned. So coming to quantum computing, even a few years back actually, this was actually a technology for the future, because we were talking about whether we'll have a quantum computer ever, when will we have a quantum computer, and things like that. But right now, we cannot really say it is a future technology anymore, because many industries and some universities, they have their own quantum computers. But yes, these quantum computers have some limitations, and they are constantly trying to upgrade it, trying to make it better and increase the number of qubits and so on. And now, just to share a thing with you before I start, I remember a story a few years back. There are many myths that surround this quantum computing, like quantum computers, when they will come, they will solve everything. A few days back, actually, I read a post in Facebook whether a quantum computer can actually solve this pandemic situation. So, no, it can't. So, and people talk like if a quantum computer comes, then all the crypto systems will be broken. No, it won't be. There will be obviously some effects, but these are like the myths that surround a quantum computer. And we'll really focus on those things, what can actually be done, and not just what can be done now or in a few years. We will not be interested in what can be done maybe 100 years from today, when we all won't be alive. And just in context of these myths, so let me just share a story with you. A few years back, I had a student, an engineering student, and we were talking about automata. And he was a very good student, a very enthusiastic student. And we were discussing about these complexity classes. And after the finish of the study, I just told him that, quantum computers, when they come, some of these problems can be solved much faster using a quantum computer. And he was very excited. He said, wow, that's excellent. And when it comes to the market, I'll be the first one to buy a quantum computer. I said, okay, that's very nice of you. But there is a property of a quantum mechanics that says that given a quantum state, you cannot really make a copy of it for any arbitrary state. So I told him that, okay, you can buy a quantum computer, but you cannot do any copy paste there. and he was devastated. So he was an engineering student, and I told him that you cannot do any copy paste using this quantum computer. He was devastated, and he said all of this is totally rubbish. Why would anyone really want to build a computer in which copy paste is not allowed? I have no use of such a computer. I'll never buy it. So these are some things that happen. But let's now jump into this. We'll first talk about some motivations. So I was already saying about that, but we'll see it in a bit more detail. What can be done in a quantum computer and what can be done now? These two questions will focus in motivation. And then we'll actually try to see an implementation of a classical problem using a quantum computer. And that problem will be MAKAUT problem. Those of you who have taken a computer science class, maybe you have seen MAKAUT problems, or maybe you have seen some NP-complete problems. These are sometimes called combinatorial optimization problems. Those who have not, don't worry, we'll walk through it step by step. So I'll just talk about those combinatorial optimization problems, especially MAKAUT problem. And then in the third section, we'll come to quantum computation. We won't go very deep into it, but we'll only talk about what we need to know. All these qubits and all these things that I was mentioning, we'll learn what those things are. And finally, in fourth and fifth section, we'll combine the knowledge we gain from section 2 and 3 together to see how quantum computer can actually solve some combinatorial problem more efficiently. So by solve, I mean some approximate solution, but we'll come to this. Now, if there is anyone who haven't heard of quantum computation, and I really want him or her to motivate that you should come and study this subject, this is awesome. How should I motivate that person? I would always start with something called Shor algorithm. Why so? Let's see. So, you know cryptography. What is crypto system? So we talk about security in day-to-day life. We have security, we do online transactions, so we don't want our card details or CVV or this OTP, this should not be accessible to anyone other than me. So that's the security I want. Even when we are doing some WhatsApp communication, you will see it is written end-to-end encrypted. So if there is an eavesdropper sitting in between, he or she should not be able to see what I am writing to my recipient. So these are the securities that we demand, and many other securities that we demand in day-to-day life. And one of the best algorithms that we have in crypto system, in classical computer, is this RSA algorithm. So RSA algorithm relies on a very simple fact that if I give you two numbers, say two big numbers, and I ask you to multiply it. Recently, this film of Shakuntala Devi has released, but you may not be able to do it as fast as her, but you can do it. You can multiply two big numbers with some difficulty, fine. But if I give you a really big odd number and ask you to find its prime factorization, this is a much more difficult task. Not only for a human, but it is a difficult task also for a computer. So RSA relies on this computational hardness. It is not true that RSA cannot be broken. Yes, RSA can be broken using a classical computer as well. But suppose I am planning something malicious right now. I am talking to my accomplice using this RSA crypto system so that someone who is intervening cannot read what I am planning actually. But if you want to stop me, if you want to stop my malicious actions, then what is the use if you just get hold of my encrypted things and then you break it a year later when all the actions are done? That doesn't make any sense. If you want to stop me now, you need to break the code now. And that is where RSA is secure, because the time required to break an RSA crypto system, or rather to do the factorization part in a classical computer, is exponential. So exponential means if n is the number of bits bits in the number that you want to factorize, then it is of the order of 2 to the power n. But here comes Shor algorithm. Now Shor showed that if you have a quantum computer, then something that would have required you of the order of 2 to the power n, essentially it's order of 2 to the power n to the power 1/3, but let's not go into that detail. 2 to the power n will require you less than order of n cube. And something that was exponential comes down to polynomial. And right now in the time of this pandemic, you know what exponential spread means. It is dangerous. So we don't really ever want exponential, and we'll be very happy with something that is polynomial. And Shor algorithm can do this factorization in polynomial time. So it means that if you have a quantum computer and you are trying to break an RSA crypto system, you can actually break it much, much faster. You don't really need to wait maybe for a year or something. You can do that in an hour or maybe something like that. So this is called, often it is called the crown jewel of quantum computing, because this was the first algorithm that made people very much interested towards this field, that quantum computer can have real, actual implications in some day-to-day life problem. But we'll take a step back. Yes, this is a motivation. This is something that a quantum computer can do, but let's take a step back. In general, in RSA crypto system, you will find a key size of 1024 bits or often bigger, 2048 bits and something. Now, without going into the detail of Shor algorithm's implementation, to break something like that, 1024 bits using a Shor algorithm, you would require around 3000 quantum bits or qubits. So what these qubits are, what are their properties, we'll see in section 3. But you will require around 3000 qubits. And then again, this circuit of Shor algorithm is really large. And when you are executing a large circuit, you all know that errors will creep in. You cannot really do anything about that. Errors will always be there. Obviously, you can do error correction. You can try to say that I'll prepare my system in such a way. In classical computer, we also do that. We'll prepare our system in such a way that if there are errors, that can be corrected. But if you want to do that, then this requirement of 3000 quantum bits exceeds 20,000 quantum bits or something like that. Now let's take a sanity check. What do we have today? IBM has a 16-qubit quantum computer that you can access right now through their cloud. They have even larger quantum computers like 20 qubits, or I think they have even 40 qubits, but that is not accessible to everyone. Google has a 54-qubit quantum chip, the Sycamore chip, using which they have published a paper on quantum supremacy last year. And they are working on a 72-qubit quantum processor. So we are right now talking of a scenario where the number of these qubits, whatever they are just quantum bits. In classical computer, you have bits. In quantum computer, you have qubits. So we are talking of a scenario right now where you have quantum bits less than 100. And if I try to motivate you with something that would require maybe tens of thousands of qubits, well, then you can just go to your industry and say that, good, you are investing so much money on this, you are paying me a large salary, you just wait for next 20 years and I'll give you a return. That will not work. You need to find some domains where you can actually apply the use of quantum computers that we have now. So that is our thing that we want. We want to take a step back. Shor algorithm is the crown jewel that we have. But can we do anything with these near-term quantum devices? So what do we mean by near-term quantum devices? The devices that we have now, or we are expecting in a few years. Not something that we are expecting 20 years, 30 years later, but in a few years. And what are the limitations of these near-term devices? Error correction is not possible, because you can see from last slide that we said that for a 3000 quantum bits, if you use error correction, it will go beyond 20,000. The qubit requirement goes beyond 20,000. So if you have a 16 qubit quantum computer, and this is basically a factor of 7, if you see. So if you use a 16 qubit quantum computer, you try to do error correction, then basically you are left with 2 qubits. And that is not really very much helpful for anything meaningful. So error correction is not really possible. The moment error correction is not possible, let's come to this third point. It means that these devices cannot execute very large circuits, because if you are using large circuits, then errors will creep in. There is nothing you can do, but you cannot correct those errors. So your solution will be incorrect. So you cannot execute large circuits. And coming to the second point, the number of qubits are small. Today we have less than 100, but maybe in a few years we'll at most have a few hundreds, nothing more than that. So these type of devices, they are either called near-term devices, or John Preskill coined this name miscu, noisy, because error correction is not possible, intermediate scale, because only a few hundred of qubits are at most possible, and they are quantum devices. So this miscu devices. And this is what we will focus on today, that using a miscu device, we cannot implement Shor algorithm. But what can we do using a miscu device? Is there anything meaningful that we can do? Obviously we can, and that brings us to this combinatorial optimization problem. So let's dive into this. Those of you who have taken algorithm or automata class will be a bit familiar with this. Those of you who haven't, let's walk through it together. Think of this very simple problem that you not only do in algorithm, but you also do in digital class as well. So these are called clauses. This is one clause and this is another clause. These are OR operations. This cup-like shape, these are OR, and this bar is NOT. So you need to find an assignment for x1, x2, x3. The values will be either 0 or 1, such that both of these clauses are satisfied. Satisfied means both of these clauses will evaluate to 1. So you can very easily do it. There will be multiple solutions as well, but let's stick to this solution that 001 is a valid solution. You can have other solutions as well. For example, say 110 is also a solution. But for this talk, let us stick with that 001 is a valid solution, and we'll come back to this problem again and again. So we need to find this type of assignments. But is it always possible to find such an assignment? No. Let's take another example. So here are the 4 clauses, and I want you to give values of x1 and x2 with zeros and ones such that all 4 clauses are satisfied. You can very easily see that it is not possible to satisfy all the 4 clauses. So do we give up? No. So we say that, okay, if all 4 clauses are not satisfiable, you find me an assignment that will satisfy the maximum number of clauses, maybe 3 clauses. So this is like an OR gate. You can see that if you give something like 1, 1, it will satisfy 3 clauses, but not this last clause. So that is our question, that these type of problems are called satisfiability problem or max set problem. That is, when you cannot satisfy all the clauses, you want to satisfy the maximum number of clauses. Okay. So why are we interested in these type of problems? These are just giving some values, zeros and ones, and suddenly why are we interested in that? Because these type of problems have immense applications in many real life problems. Like you have this vehicle routing problem. What is this? You use it in Google Map. You want to go from location A to location B, and there are many paths, and some of these paths, maybe they have traffic, huge traffic, bad traffic, and some paths have one way. So what is the best path that you should take from position A to position B so that you can reach there fastest? So these are some vehicle routing problems. Then you have job scheduling problems. Suppose you have an industry and you have 3 or 4 machines, and multiple jobs have come in, and those machines have a capacity, how many jobs they can execute or something like that. And these jobs that has come in to you, they have some time requirement. So you want to schedule the jobs in such a way that the maximum number of jobs can be processed using those machines. And remember, those machines in a single day can run only for say for 30 hours or sorry 30 hours, what I'm saying, say for 15 hours or something in a day. So this type of job scheduling problem. And then suppose you have this art gallery or a museum where CCTV cameras are to be placed. You want to place the CCTV cameras such that by using the minimum number of CCTV cameras, you can actually monitor the entire museum. So all these problems, and there are many problems related to artificial intelligence that can be related to this SAT problem. So that is why this SAT or max SAT version is extremely interesting. But these problems are really hard, and they fall in a class that is called NP hard. So if those of you who don't know NP-hard, if I tell you something is NP-hard, you might as well give up any hope of finding a good polynomial time algorithm for it. So that is kind of, it is not a definition of NP-hard, definitely, but that is how you can think of NP-hard. So do we give up? We can't give up because these are some problems which are used in day-to-day life. So what we do, we say that, okay, I cannot afford exponential time, but definitely I can afford polynomial time. Give me an algorithm that may not find me the best solution, but it will find me a good solution, a near best solution. For example, suppose if you have this job scheduling problem and the best algorithm, which would require exponential time, can process 30 jobs, and it will require maybe an hour to run this algorithm. But I come and tell you that, okay, I have come up with an algorithm that will require just 5 minutes to run. It may not be able to give you a scheduling that will allow you to process 30 jobs, but it will definitely give you a schedule that will allow you to process at least 26 jobs. You should be happy with that because I am just reducing the computing time from 1 hour to 5 minutes. So that is the idea of an approximate algorithm. And what do we mean by approximation ratio? We mean that for any input that you give me, suppose this approximation algorithm about this job scheduling problem that I am saying, maybe for some instance my algorithm is able to give the best solution, for other instance it is not able to, but I should give a guarantee that what happens if a certain number of jobs come and I turn up with a schedule that can only process 5 jobs. That is not going to work. So I should give you a promise that irrespective of whatever you do, whatever input you give me, my algorithm will never process number of jobs which is less than, say, 25. So that is a guarantee that I should give you. It can process more than 25 jobs. It can even process 30 jobs at some points, but it will never process anything like 24 or 23 jobs. 25 is the lower bound. If I can give you this guarantee, then this 25 divided by 30, it is called the approximation ratio. And obviously, we want this approximation ratio to be as close to 1 as possible. Because if it is 1, that means I am giving you the optimal solution, the best solution. Fine. So the problem that we'll look into is called this MAKAUT problem. What is this problem? It says that you are given a graph G, where V is the set of vertices. You need to partition these vertices into 2 sets, A and B. No vertex can be in 2 sets at the same time. But you need to ensure that your partition is such that the number of edges crossing from this A to B is maximized. For example, take this picture. So this is a graph, and here we say that suppose this black is partition A and white is partition B. So the way we have done it here, only this edge is not included in the cut. Otherwise, all these edges are included in the cut. So you need to find such an assignment such that the size of the cut is maximized. This is the MAKAUT problem, and it is a really tough problem, and it has many applications. Now, the best known algorithm in classical computer is called this GW algorithm. It is Bowman-Williamson or something like that. That gives an approximation ratio of 0.878. So what does that mean? That means that if the best solution is, suppose the cut size is 1000, then I'll always give you a cut. This algorithm, this GW algorithm will always give you a cut whose size is at least 878. It can be greater than that, but it will be never less than that. And the time requirement is this mod V means the number of vertices. So if n is the number of vertices, then order of n squared is the time requirement. Now, we'll try to see how this problem can be solved using a quantum computer. Not solved again. It can be solved approximately using a quantum computer. But before that, let's just dive into what quantum computation is very shortly, only what we will need here. So again, remember, this was the problem we talked about first, and we saw that 001 is a valid solution. So how do you actually solve this type of problems in a classical computer? You will try out all possible combinations, and there are 3 bits. So the number of combinations is 2 to the power 3, that is 8. So you will try out all possible combinations, and in the worst case, you will have to try out all the 2 to the power 3 combinations to find the assignment, the perfect assignment here. But what can be done using a quantum bit? So a classical bit is either 0 or 1. This is suppose a picture of this classical bit. A quantum bit, interestingly, so this is called this gate notation, this funny notation. Don't bother about it much. Just think of it as a funny notation to represent 0 in a quantum computer. So this quantum bit can be either 0 or 1, or it can be in a linear superposition of them. So this is roughly translated, this psi is some alpha 0 plus beta 1, while this alpha beta are complex. So if you see this picture, it shows that it can be 0, it can be 1, it can be something in between. Now this something is in between is often something we say that it can be both 0 and 1 at the same time. That is somewhat a very loose talk. It is not mathematically entirely correct, but you can think of it in this way. It doesn't really harm a lot. If you say that a quantum bit can be both in 0 and 1 at the same time. So that is something interesting about quantum computers. So what can we do with it? How is it useful? So we want to solve this problem, right? And we take 3 qubits, x1, x2, x3. And then we create this equal superposition. So remember, each of these qubits can be both in 0 and 1 at the same time. So if I take 2 qubits, they will be in 0, 0, 0, 1, 1, 0, 1, 1 at the same time. If I take n qubits, they will be in all 2 to the power n combinations at the same time. So if I take these 3 qubits, it will be in all 2 to the power 3 combinations at the same time. Now you compute this function f on this state psi, on this superposition state psi. What happens? All the 2 to the power 3 combinations are computed at once. So what would have required you 8 tries, now it will just require you a single try. You just apply this function f once on this superposition state psi, and all 2 to the power 3 combinations are computed at once. So this is a tremendous power of quantum computer that you don't have in classical computer. You can never have in classical computer. But this brings up a question. So if this is possible, then anything and everything can be done in a single shot. But I said in the beginning that there are many myths. Not everything can be done using a quantum computer. So there must be some catch here. Everything cannot be done in a single shot. So what is the catch? The catch is this measurement postulate. It says that you can obviously create a quantum state qubit in this superposition state, but finally you will have to measure it. You do this type of computations, something happens, but then you will have to measure it to know the outcome. What is the outcome? But when you measure it, the state will collapse to 0 or it will collapse to 1. And it collapses to 0 with probability mod alpha square. It collapses to 1 with probability mod beta square. Right? So a complete description of a qubit, here I just wrote that a qubit can be in superposition and alpha beta is complex, but there is one more criteria that you must take into account, that is mod alpha square plus mod beta square should be equal to 1 because they are probabilities. So the total probability should add up to 1. Now what does this mean? So let's take a quantum state. This is a valid quantum state. What will happen if I measure this state? So we said that we'll get 0 with probability mod alpha square. So this is a real number, so the modulus does not come in. The modulus is only necessary when we have complex numbers. But we get 0 with probability square of this, that is 1/3, and we get 1 with probability 2/3. So this is 0.33 and this is 0.66. And if you simulate this, you will see this is the result. Right? So this is just 0.328. Slight variation is obviously probable because this is probability, and this is 0.672. So the problem is, although we can compute all the 2 to the power n combinations at the same time, when we measure it, we only get one of it. So there is no guarantee that you will get the best solution, because remember that we want the solution 001. So I create a superposition and I operate that function. Everything happens at the same time in one single shot. But how do I guarantee that when I measure, the outcome will be 0, 0, 1? Because this is probabilistic. There is nothing you can do about that. So the general idea of a quantum algorithm is that you create an equal superposition of states and then you try to increase the probability of the desired outcome. For example, in this here, if the desired outcome is 0, you can see that actually you will receive 0, you have a higher probability of getting outcome 1. So you have to do something such that these values change. You have to increase these values so that this probability increases. And that is the idea of almost every quantum algorithm. So let's look into it a bit detail. So again, this was the problem we wanted to solve. We create an equal superposition. What do I mean by equal superposition? All the states are equally likely. So if you see, this is 1 over 2 root 2, square of that gives you 1 by 8, 1 over 8. And there are 8 states. So each state, you will obtain each state with probability 1 over 8. So if you measure it right now, you can receive any of these states, right? You can receive any of the 8 states. So it doesn't really guarantee you that you will receive this 0, 0, 1, which is your desired state. So we'll have to do something, and this something is the algorithm, such that it will change the superposition state and the probability of obtaining this 0, 0, 1 will be extremely high. This is the idea of a quantum algorithm. But how do we do that? We have seen what a qubit is. So we now need to change these qubits. So this algorithm do something, we need to do something to this qubit. How do we do that? So here comes the idea of some operations. If we just create a qubit and keep it as it is, nothing will happen, nothing interesting happens. So the quantum state must evolve. So we need to add some operators on these quantum states, and we call these operators quantum gates. Just like in classical computer, you have classical bits and classical gates, and or not, NAND. Similarly, you have in quantum computer some qubits and some quantum gates. So ideally, these are unitary operators, but we'll not focus into that too much. One very important gate is this Hadamard gate, because we have been talking about how to create an equal superposition. So you see this Hadamard gate creates from 0, it takes to an equal superposition of 0 and 1. Why is this an equal superposition? Because the probability of getting 0 is half and the probability of getting 1 is also half. So it is equal superposition. Similarly, if you take the state 1, it will take it to 0 minus 1. So this 1 here has a phase of minus 1. If you can visualize it, this is something called block sphere. Let's not worry about its mathematical details, but it is very nice for visualization. So a qubit 0 is actually denoted like this up arrow. So this is this 0, and qubit 1 is denoted like this down arrow. This is 1. So the moment we apply this Hadamard gate, what happens is now 0 goes to this. This is actually an equal superposition of 0 and 1. You can see it is in the midpoint. And similarly, this 1 goes to 0 minus 1. You can see it is also in the midpoint, but in the opposite direction. So this is a minus phase here. Another gate that we want to talk about, so this is a Hadamard gate, the single qubit gate, and then another gate is C0, which is a 2-qubit gate. So this is the notation of a C0 gate. These two gates will be important as we move on. So hopefully this is clear to you. What C0 gate does, this first qubit is called the control qubit, and this is called the target qubit. So this solid round is the control, and this plus is the target. If the control is 0, nothing happens to the target. First and foremost, the control never changes. The control remains as it is. So it is 0, 0, 1, 1. The control, even after applying C0, it remains 0, 0, 1, 1. And if the control is 0, the target remains unchanged. So here we have control 0, the target is 0, 1, and the target remains 0, 1. But if the control is 1, then the target is flipped. So here the control is 1, target was 0, control remains 1, the target is flipped to 1, and here the target is flipped to 0. So this is called a C0 or a controlled knot. The full name is controlled knot. And because this is a knot operation, you see the 0 goes to 1 and 1 goes to 0. That is why it is knot, and it is controlled because that action of NOT gate is controlled by this control qubit. That is why it is called controlled NOT or C-NOT. And there are some parameterized gates. What I mean by that is that these gates actually take different values. These gates are actually matrices because we said unitary operators. These gates are matrices, and depending on the value of theta, the value of the matrix will change. That is why it is called parameterized gate. So without again going into this highly complex mathematical form, let's see an example. Suppose we have this qubit here. We start with 0 state, and then we start increasing theta from 0 to 2 pi. So this is the y-axis, right? And this is ry. It means rotation around y. So think of a stick going around this y-axis. What will happen if you just start to rotate this stick around this stick which is around this y-axis? You are just starting to rotate it. So this thing will come down like this. That is what should happen, right? And we'll see exactly that happens. So this is how, when I change theta from 0 to 2 pi, the state will change. So if you see again, so you can just visualize it like I am having a stick here around this y-axis. I am turning this stick like this, and the state keeps changing. Similarly, you can have rotation around z-axis, you can have rotation around x-axis, but these are all called parameterized gates. And we'll use these three types of gates in our algorithm: the Hadamard gate, the C-NOT gate, and this parameterized gates. And there are many other types of quantum gates as well. We'll not discuss that, but you can check it out in some textbook, or this is basically IBM Quantum Experience page. Okay, I am not promoting any industry or any brand here, but this is a really nice visualization. These are many gates. You can just drag and drop these gates on the qubits, and you can see their actions. And these are the measurement probabilities. You will directly get the measurement probabilities. And this is something called a Q-sphere. Let us not think about that for the time being. Maybe the next speaker will mention it a bit. But you can just go to this IBM Quantum Experience page and play around with it. It's really nice. Fine. Okay. So is there any questions till now? Because we'll move to a bit different domain right now, and we want to combine both of them together.
No questions have still been asked. So if any question comes up, I'll ask you. So you can continue at this moment.
Okay, good. So that means either you are understanding everything or you are understanding nothing. Good, good. Okay, so let's start with this variational quantum algorithms. What are they? Why are they important? So we'll again take a detour. The detour will be slightly not really taking, so this section will actually combine these two, but we need to take a slight detour. So I'll ask you to please hold on with me for some time. So this variational quantum algorithm, the idea is that suppose you have this type of operation. It is a sigma z operation, and I want to find the ground state. What do I mean by ground state? So this is a matrix, and you will have eigenvalues and eigenvectors. So if you actually work out, it is easy to work out the eigenvalues and eigenvectors of these matrices. You will see that the eigenvalues are +1 and the -1, and the eigenvectors corresponding to this +1 is this 0, quantum state 0, qubit 0, and for -1, it is qubit 1. So my goal here is I want to find this state 1, that is corresponding to the minimum eigenvalue. Fine. Why is it important? Let's see. And the next question is, why is it difficult? Because you can easily calculate the eigenvalue and eigenvector of this matrix. So why am I so worried about this? The reason is there can be two issues. I can just give you a circuit and I have done some operation I haven't told you. So you don't know the operation is sigma z. So you cannot calculate if you don't know. And the second thing is, who is saying that we are only interested in a single qubit? We may have multiple qubits, and to solve real life problems, we require multiple qubits. And if we have a n qubit system, just like for a single qubit system, we have a 2 cross 2 operator. Similarly, for an n qubit system, we will have a 2 to the power n cross 2 to the power n operator. Fine. Now, just think of it. If n is even, say, 3, it is an 8 cross 8 matrix. It is, I won't really like to do the calculation of eigenvalue and eigenvector on hand. And even as n becomes, say, n equal to 30, it is not a very large number, because, you know, where will we apply this type of algorithms? On social networks or something, and n is the supposed number of users there. What is n equal to 30 in a social network? I have much more friends in my Facebook actually. So n equal to 30 is a very small number, but even for that, it is intractable for classical computers to compute the eigenvalue and eigenvector. So we need some other techniques. What technique can we use? We can make a guess. So this guess is called an ansatz. So we'll make a guess using a parameterized circuit, because our guess may not be very good. So we'll just make a guess and we'll see whether it is a good guess or not. And if it is a good guess, fine. If it is not, then we'll change the value of the parameter and see whether this change actually gives me a better state. Fine. So this is the idea, and we vary this value of parameter, and we'll vary in such a way that we get close to the result that we want. So let's take example. Again, ry theta is our guessed answers. The actual the operation that we did was sigma z. I have no idea that sigma z was operated, so I am making a guess. Let the guess be ry theta. So can we just put any value of theta? Obviously, you can understand that any value of theta will not work, because suppose I put theta equal to pi by 2, then this becomes an equal probability of getting 0 and getting 1. But I am much more interested in getting 1. It is not a good idea if I have a circuit that will give me, say, in 100 times, it will give me 50 times 0 or 50 times 1. So I want the probability of getting 1 to be very high. And if you just work out, this is a very simple simulation, you can see that there are indeed values of theta just beyond 3. It is 3 point something, just beyond 3, that will give you an exactly probability 1, that is with certainty you will get the ground state, that is the state 1, this state, this quantum state 1. With certainty you will get quantum state 1 if you can apply theta to be 3 point something. So this is the idea of a variational algorithm, is that you start with a guess, then you start changing, you see how good your guess is, then you start changing the value of these parameters so that your solution comes close enough to the actual solution. Why we are saying close enough? Remember from our previous discussion, we said that these problems are NP hard, or if it's decision problems are NP complete. And these problems cannot be solved efficiently in a classical computer, and there is yet no proof that these problems can be solved efficiently. Efficiently means polynomial time in a quantum computer as well. So we want a close enough solution, that is approximation. So can we just start with any guess? Obviously it won't work. You can just try to see that if you start with a guess which is rz theta, and if you start with a quantum state 0, you can change any value of theta, but it will never vary from 0 to anything else. It will never get to 1. Forget 1, it will just never change from 0. So this is not a good guess. So we have two problems that we need to mind. First is, I need to have a proper ansatz. I cannot just randomly guess something. I need to have a proper technique of guessing. And we should not have many parameters. I am talking about ry theta, it is a single parameter. But again, when you go to a large graph or something like that, where n is high, it is possible that you will require many parameters, theta 1, theta 2, say up to theta k. But if these parameters, the number of parameters is extremely high, then what will happen is that you, in order to find the best values of these parameters, it will take you a long time. And finding these best values you will do in a classical computer. And even in a classical computer, it will take a huge time. So we don't want a large number of parameters, and secondly, we want a proper way to guess. So that is something how variational algorithm works. And the second question is, why do we care? Why suddenly I am interested in this type of variational algorithms or something? So let's talk about applying this variational algorithm in some sort of optimization problem. And these two problems, the vertex 2 coloring and max cut, they are equivalent. I'll talk about that, but it will be easier to show this using this vertex 2 coloring. What is a vertex coloring problem? You are given a graph, you are allowed k colors, and you need to assign a color to each of the vertex with one condition, that no two neighboring vertices should have the same color. By neighboring vertices, I mean for an edge, the two vertices should have different colors. So this is the vertex coloring problem, and it has huge application in scheduling. Suppose when you are scheduling a routine, or when you are scheduling maybe IPL, EPL, whatever, and this has huge applications. But here we are interested in vertex 2 coloring. That means the number of colors is 2. So here it is black and white. You need to give colors, only 2 colors you have, you need to give these colors to these vertices. Fine. So obviously you can understand that for every graph, it may not be possible to satisfy this constraint I said, that you cannot, for a given edge, you have to give 2 different colors to the different vertices. It is not possible always to satisfy it for every edge. For example, here, this edge, you cannot satisfy it. So what is the idea? Remember from earlier we said that if you cannot satisfy everything, try to find an assignment that will satisfy the maximum number of constraints. So here also, you want to find a coloring that will satisfy the constraint for maximum number of edges. And in fact, this is actually such an assignment. And if you just remember from earlier, this is exactly the max cut. This is exactly the max cut solution that we have been seeing for so far. So if you can find out the best vertex 2 coloring for a graph, then the number of disagrees, so this is called a disagree. Here I should have one white and one black, but unfortunately I was forced to give both of them black. So this is a disagree. So if I can find a vertex 2 coloring with the minimum number of disagrees, then it is equivalent to finding the max cut for a given graph, because the number of agrees is actually equal to the max cut. Because we said that for max cut, you need to assign each vertex to some set. So you can think that black is set A and white is set B. Good. Now, this is something called an Ising formulation of a problem. This is a classical problem used in classical computer. How do we take it to a quantum computer? Obviously, we say that for every vertex, we associate a quantum particle here. Forget the spin up, spin down. It is a qubit associated with it. The qubit can be either 0 or either 1. In other words, you can think, suppose if it is black, it is 0. If it is white, it is 1, or vice versa, right? So what we want, that if there is an edge UV, if U is 0, then V should be 1. Or vice versa. If U is 1, then V should be 0. This is what we want. And we want it for every edge. Whether it is possible for every edge or not, that is a different question. But ideally, we want it for every edge. Now we are taking this problem from computer science to a bit of quantum mechanics. So how does it work? Think of 2 magnets. What we want here, we wanted that both of them should not be the same color, or in other words, both of them should not be 0 or both of them should not be 1. But if they are somehow, what happens? Think of a magnet. If you just hold 2 magnetic north poles close enough, you can actually feel a force of repulsion. They are trying to repel, but you are just forcing them close together. If you just leave it, they will just go apart. So the same thing we'll think about here, that if we cannot satisfy this property for a particular edge, then there will be a force acting along that edge. And if we can, there will be no force. So you can think of it like 2 magnets, north pole taken together. So there is a force acting along this black edge, And for here, this is North Pole, this is South Pole, so there are no force acting along. So we are not interested in like that attractive force. For the time being, think only of repulsive force. And these two are trying to repel, and these two are okay. There is no repulsive force here. So this is the physics idea of this classical problem. And the promise is that if you can find a configuration with minimum force acting along all the edges, what does that mean? See, here I want to find a configuration such that minimum number of edges will disagree. So that means if there were another edge that was disagreeing, so there will be two forces, but rather we want such a configuration that the number of forces is minimum acting around the edge. And this, if you can find such a configuration, this corresponds to the ground state of the system, and this is also the solution to the optimization problem. Now this is a promise. So that is why we are interested in this. We want to take a classical computer and rewrite it in this form, this is called Ising formulation. So rewrite it in the Ising formulation, and we want to find the ground state of it. So hopefully now things are coming together for you. For finding the ground state, we cannot do it directly, so we need to use those variational principle. Okay, so let's move into our final section, which is this quantum algorithm for MAKAUT. So just recall once more that MAKAUT, the problem is that you are given a graph. You need to partition V into two sets, A and B. Now this A union B is equal to V. That means each and every vertex should be in one of the partitions, and this means no vertex can be in two partitions at the same time. And then doing that, you want to maximize the number of edges crossing from A to B. So we'll take it to its Ising formulation. So we say that with each vertex V, there is an associated qubit. Now this qubit can be either 0 or 1, just as discussed before. Now let's think of an operator sigma z. The property of this operator is, if the qubit is 0, then it gives an eigenvalue of +1. If the qubit is 1, it gives an eigenvalue of -1. It does not change the state. So this is a property of sigma z. It does not change the state. Whatever the state it remains as it is. But if the state is 0, then the eigenvalue is +1. If it is 1, then the eigenvalue is -1. Now, for a single edge, UV, we create this operator. This operator is called Hamiltonian, but don't worry about names because scientists like to give fancy names. So this is called a Hamiltonian operator for this particular edge. And let's see what it does. It's a mathematical formulation, but it does a very simple thing, a very, very simple thing. Sigma z u implies this sigma z is applied on the qubit u. Now suppose both u and v are in the state 0. So that means the eigenvalues are +1, their product will be +1, and this will become 0 because 1 minus 1, that becomes 0. Similarly, if both of them are 1, if both u and v they are this state 1, then the corresponding eigenvalues are -1. Again, the product is +1. Again, the product is +1, so it becomes 1 minus 1, 0. But if one of them is 0 and the other is 1, then one of these is +1, then the other is -1. The product is -1, and this becomes +2. Because this product becomes -1, and here is a minus before, so it becomes +1, and this becomes +2. And this half is just used to normalize it so that this +2 becomes 1. It doesn't really matter if you don't give this half. So this operator simply states that if both the qubits are in the same state, either 0 or 1, then there is no contribution for this operator because we were getting a 0. And if the one qubit is in 0 and the other qubit is in 1, we really don't care which one is in 0 and which one is in 1, because u can be in 0, v can be in 1, or vice versa. But if they are in the different states, then this HE contributes +1. So for disagree, because disagree means that we are coloring both the vertices the same, or we are assigning both the same magnetic pole or something like that. So if it is a disagree, then there is no contribution, it gives a 0. And if there is an agree, then it contributes +1. So the idea is you apply this HE for each and every edge, you take the summation. Now you find an assignment of 0 and 1 such that this summation is maximized. So hopefully this is clear. For each edge, if this is clear, then this should be also clear. For each edge, you create this operator. It will give a 1 for disagree. It will give a 1 for agree. It will give a 0 for disagree. So you do that for all edges. You take the summation, and now you find an assignment of 0 and 1 such that this summation is maximized. So this is the idea of a max cut problem. So now from what we have seen before, we have found the operator HP. This is again called the Hamiltonian operator, and we want to find its ground state. But see, this is an NP-hard problem, and we already said that using a quantum computer, you cannot just solve an NP-hard problem so easily. So it is not really so easy that if I give you HP, you will immediately tell me what the ground state is. That is not done. So again, we'll have to take use of some variational principles or something. So we cannot prepare the ground state of HP. This technique is called Diabatic Theorem. So we have prepared HP here, but we don't know how to find the ground state of it because it is difficult. If it were easy, the problem wouldn't have been NP-hard. So the idea is, if you remember from previous section, we said that idea of any maximum quantum algorithms is that you start with an equal superposition and then you try to reach your desired state. So obviously we'll start with an equal superposition of all states here. It is easy to prepare. And the Hamiltonian corresponding to this, we call it HB. We'll start with here and we want to reach the ground state of this. How do we do that? The adiabatic theorem comes to our help. It says that you prepare a Hamiltonian in this. We'll explain it in just a moment. It is very easy. It looks difficult, but it is very easy. It says you prepare a Hamiltonian in this state and you vary this capital T from 0 to small t. What will happen if we do that? When capital T is 0, this second portion, this becomes 0 because capital T by T, this is 0. So HP becomes 0 and this is 1, HB. That is what we said right now, that you start with HB, whose ground state is this. And it is this mathematically, it is saying the same thing, that when capital T is equal to 0, you are actually having HB, nothing else. And when capital T is equal to small t, see this portion becomes 0 because this is 1 minus 1 is 0, and this portion becomes 1. And again, this is precisely what we said, that you start with HB and you want to end up at the ground state of HP. So what we stated here in words, it is just expressing it in mathematics. So that is not very difficult. Here is a trajectory that starts from time t equal to 0 and moves to time small t. But the catch is this, slowly enough. You need to do this, you need to move along this trajectory slowly enough. What do I mean by slowly enough? So let's see that. Again, don't go too deep into these mathematical terminologies. I'll just state what it means in simple words. So take this capital T by small t to be S. So all these scientists are really lazy, so they don't want to write capital T by small t again and again. So they are replacing it by S. We start with the initial state psi 0 and we move to a final state psi t. Now it says that for every time instance capital T, so S varies from, see, capital T varies from 0 to small t. So when capital T is equal to 0, this T by T is 0, and when capital T is equal to small t, T by T is 1. So we can say that S varies from 0 to 1 actually. So for every value of S, E0S means the eigenvalue corresponding to the ground state, that is the minimum eigenvalue, and E1 is the second minimum eigenvalue. So if the difference of E1 and E0 is greater than 0, again we'll not dwell much in this, but there can be some situations where this is not greater than 0, but it becomes equal to 0. That is something called degeneracy. Let's not talk about that. But if you can guarantee this condition, then as you take this time to infinity, the initial state will settle in the problem, in the ground state of our problem Hamiltonian. So this mathematical terms basically states that the overlap of the initial state after the evolution and our required state is 1. That means they become the same. But that is not the problem. It says that the time t should vary as inversely proportional to this g mean square, where g mean says that if you vary s from 0 to 1, then you take the value of E1s minus E0s at every point and find the minimum of that. If you can do that, then your time that we said here slowly enough, so this time should be proportional to 1 over g mean square. Now there are two difficulties here. First, it is sometimes very difficult. Why sometimes? It is most of the time very difficult to actually calculate this. Analytically, you cannot calculate, and most of the papers try to do it numerically. And second thing, for NP complete or NP hard problems, this actually varies at as order of 2 to the power n. Or in the other hand, I shouldn't say this actually varies, but rather the time, this 1 over g mean square, because this E1s minus E0s becomes very, very small, very close to 0, and this t suddenly shoots up. So that is what happens for NP complete problems. So that is the adiabatic algorithm, and that is the use of it. It helps us to go from this state, from this start state to this final state. But obviously it has some limitations, because if it didn't have any limitations, we already have a solution. There is no point talking about approximate solutions. So we'll move to approximation now. But there is one more thing. That is, we talked about quantum bits, we talked about quantum gates. But this adiabatic thing, there was nothing about quantum gates. It says that you prepare this Hamiltonian, you vary it along this trajectory. So how do we actually fit it into the gate model that we have already learned? And this QAOA that we showed, quantum approximate optimization algorithm. So if you remember, the start of this was quantum algorithm for MAKAUT and QAOA. This QAOA actually tries to take this same concept to gate-based quantum computing. So let's see that. The idea is simple. Those of you who have taken a computer science class, there is something called analog to digital computer. For example, now that I am talking this audio, the video that you are seeing, all of these are analog signals. But our computer can understand only digital signals, zeros and ones. So how do you convert this? You do some sampling at some spaces, and you take the values of the samples there. This is the idea of sampling and changing from analog, this analog, to this digital value. Now, if you actually sample at only a few places, you can do that. But then your approximation will not be very good, because if I sample one in this peak and sample one here, the approximation will not at all be very good. But if I increase the number of samples, then ideally the approximation will be very good and very close to this analog signal. And theoretically speaking, if you can sample at every point, that basically means that you are just building this analog signal. Obviously, we cannot sample at every point, and so we have to look into some approximations. Here also, this is a kind of analog signal. This is a kind of continuous trajectory. So using quantum gates now, we'll break this trajectory into discrete steps. So how do we do that? We prepare each qubit in this superposition state. That is our starting point. We start with equal superposition of all states, and we have seen how to do that. If Q0 and Q1 are both in 0, then we just apply a Hadamard gate. Now think of it, what it means physically. It means that every qubit initially has an equal probability to be in partition A or partition B. So if it is in partition A, suppose we say it is in the state 0. If it is in partition B, we say it is in state 1. So initially, all the qubits has an equal probability to be in partition A or in partition B. And this we achieve using these two Hadamard gates. Now the depth of this circuit is 1. Two things. What is depth? You take a circuit, you go from the starting point to the ending point, and the longest path, that is the maximum number of gates along a single path, gives you the depth of the circuit. So here for both the paths, there is only one gate, so the depth is 1. Why do we care about depth? I don't know if you remember right now, but initially in the very beginning, we said that for near-term devices, we cannot really run a very long circuit. In terms of this, we cannot really run a very deep circuit, because if we try to do so, errors will creep in and it will just change everything. So we need to make our circuits small. So that is why for these type of algorithms, we are really interested in the depth. So the initialization step requires a depth of 1. So that is the best we can do. You cannot go beyond depth 1. Now we need to break this analog trajectory using quantum gates. And we will prepare two quantum gates, this UHP and UHP. Now see, these are parameterized gates. Gamma and beta are parameters, and we can vary it. If we vary gamma and beta, the gates will change. Fine, we'll see what these gates do. But don't worry for it, we'll see just now. But these are the two gates that we'll use, that will operate one after another to break the analog trajectory into discrete states. So this is the UHP gamma. If you want to realize that, you require two CNOT gates and one RZ gamma operator. So we have explicitly seen RY, but this is RZ, rotation along Z axis. And gamma is the parameter which we can change. For this simulation, I took gamma equal to minus 2.19, but you have to find out the best gamma. So for each edge, you need to apply this UHP gamma. And obviously, so for each edge, the depth is only 3. You require 3 gates to implement this UHP gamma. And if there are m edges in a graph, you need to apply this UHP gamma on all of those edges. So the depth of the circuit becomes order of m. So again, there is hardly anything you can do better, because if there are m edges, you need to do this for that. Third is this UHP beta. So what these do will come next. What are the intuitions of having these operators? But UHP beta can be realized using single Rx operator. So this is again a parameterized operator, rotation along x-axis with beta as the parameter, and it is acting on each and every qubit. So this Rx here for my simulation, I took 0.862. And again, the depth of this circuit is 1. So we now have a total circuit. So this circuit is for a graph that has a single edge and two vertices. Q0 and Q1 are the two vertices, and there is a single edge. So for this graph, this is the entire circuit. You need to apply this circuit. This is the initialization. This is UHP, and this is UHP. Now, the number of iterations, that is the number of times we use UHP and UHP, this is basically denoted by this P. This P is a variable that is used. P denotes the number of times we are using UHP and UHP. Fine. So here we have used it only once. So this is for P equal to 1. And the depth of the circuit is order of m plus 1. Okay, you can say from computer science that order of m plus 1 is actually order of m. That is true, but this is how it was mentioned in the original paper. So I did that as well. So this is the QAOA circuit, the initialization, the UHP, UHP. And if you want to be P equal to 2, you will just have to repeat this again and again. Initialize once, repeat this again, followed by this, and so on. So this is the QAOA circuit, but what does these gates actually do? We have this trajectory, right? And we want to break it into discrete states. So UHP and UHP, so this gamma and beta, you can think of them as time duration or the length of this line. So UHP and UHP are actually breaking this trajectory into two discrete states. So obviously, as we discussed before, for a continuous trajectory, if we are sampling only at one point, it will not be a very good sample. It will not be a very good approximation. That is what we see, that this was the actual state and what we received is somewhat here. But if we increase the number of iterations, that is, if we apply this UHP and HP again and again, what will happen here is, so this is for p equal to 2. You see, the approximate state comes close to the actual state. And here is a promise that as you try to increase, as you go on increasing the number of these iterations, this QAOA becomes equivalent to quantum adiabatic algorithm. So this is exactly what we saw in our analog to digital conversation. Sorry. Okay, so if that's fine with this, let's move on to the entire algorithm. So we had a few problems with near-term devices. We cannot run a really big circuit. We do not have a large number of qubits. This issue I'll talk about a bit later about this. We cannot have a large number of qubits. But the idea is that we cannot run a very deep circuit. So here, the idea for any variational algorithm is that you take help of classical and quantum both. Whatever you can do in quantum that will give some speed up or some betterment, do it in quantum. Remaining, you do it in a classical computer. In such a way, what happens? The circuit for a quantum computer remains small. So these steps, whatever is written classical, you could have done it in a quantum computer as well, but why bother? Because the first state is you initialize these beta and gamma parameters. So if you have p many iterations, there will be p many beta and p many gamma. So you initialize them randomly. These are random number generators, right? And you can just do that in a single line of Python. Why would you bother to take this to a quantum computer? So you don't do it in a classical computer. Now you initialize the state, you construct this state, and then you measure the state. These are something you need to do in quantum because these use quantum principles and so must be done in a quantum computer. Now, when we come about measuring this state gamma beta, you need to do this measurement multiple times. By multiple times, we mean that you need to prepare this initial state again. So you fix a set of parameters, you prepare the initial state, you prepare this state gamma beta using that same parameter again and again, and you measure it. Because since it is probabilistic, if you do the measurement only once, there is a probability that you may end up with a very bad solution. So you do it multiple times to get a better estimation. So now when you measure this gamma beta, what will happen? This state will collapse to some 0, 1 and something. So that is a candidate solution. Now when you get this 0, 1, 0, 1, whatever pattern you received, you calculate the size of the cut. This can be done in a classical computer. Then you need to optimize beta and gamma, and you do this step again such that you are expected to get a better solution in the next iteration. This is the idea of quantum approximate optimization and in general for any variational quantum algorithm. And you can repeat these steps polynomially many times because we don't want exponential, but we can obviously give polynomially many times, right? Now, two questions can come up here. This is the algorithm design. So when I read it also, two questions came up that, okay, this seems like some sort of magic. Does it at all work? And if it does, why does it work? And we'll just answer these two questions right now. If it works, why does it work? And does it really work? So let's show you one simulation here. Remember, this was the graph that we were talking about. There are two vertices and there is a single edge. What is the best possible cut you can have? Obviously, if you say this is 0, this is 1, or this is 1, this is 0. Both is valid. You can have 0, 1 or 1, 0, any assignment. So we have already seen that this is the QAOA circuit for this graph. And then if we execute this circuit, so what we don't want is 0, 0 or 1, 1, right? We want 0, 1, 1, 0. So if we just run this circuit, this is the solution that we get. So you see, we get 0, 1 or 1, 0 with equal probability. And both are valid. We don't get actually 0, 0 or 1, 1. But let's not fool you with this example. because this is a very simple example, and that is why with a single iteration, it is giving you the best possible solution. But if you move to much complex graphs, much larger graphs, then you don't really expect that in p equal to 1, you will always have the best possible solution. But what we want is that the solution that has the highest probability, that is what is your expected solution, it should be very close to your optimal solution. That is how approximation algorithms work, right? Now the question is, why does QAOA work? So we have seen that QAOA work. Even if it seems like magic somewhat, it works. But why does it work? So this is a bit of physics here. It will be only for this slide. So this is a Schrodinger equation. And if you solve this, you have some sort of psi t is something like this. And here what we have is that if you see UHP, UHP have this exponential minus I gamma HP. And here Schrodinger equation says it is some sort of same. So gamma and T. So gamma, this parameter, is actually some sort of this time. That is what we also saw when we were breaking the analog trajectory into digital trajectories. It says how big the length of the line should be. Or in other words, it says how long you should operate this operator. Fine? So basically what UHP is doing, it is taking the initial state and driving it towards the final state. But then the question is, why do we need UHP? UHP is already doing this work. The reason for that is, and I encourage you, if you find this interesting, check out this website, mastythoughts.com. It is a brilliant blog and it explains this brilliantly. The idea is that suppose at some point, at some t dash, which is not the final state, you reach an eigenstate of this operator. What is an eigenstate? If you act u on v, this state v does not change. So if it reaches an eigenstate, then no matter how many times you start operating this again and again, it will never move from this eigenstate. Because you see, this u acting on v cannot change v. So once you have reached this type of v, if you act this u again and again, it will not change the state. So what this the use of this UHP operator is that it removes the system from any local optima. Good. So now that you know that, a question can come to your mind. This seems very similar to simulated annealing. What we do in simulated annealing is that we want to avoid local minima and we want to settle down in a global minima. So here is what I am saying, that it can get trapped in a local minima. So you are using this UHP beta operator to remove it from local minima and drive it towards the global minima. So the question is basically this QAOA simulated annealing in disguise? So just by using a lots of mathematical terms and quantum computing, is it that we have just turned up with simulated annealing? The answer is no. Because at p equal to 1, the probability distribution that is generated by QAOA, probability distribution of what? Of the candidate solutions. This probability distribution, if you want to simulate it using a classical computer, you use a simulated annealing or you use any other sort of algorithm or whatever in a classical computer, you cannot generate this probability distribution at a single iteration unless p is equal to np. And for most of the computer scientists, they think or they believe that p is not equal to np. So unless p is equal to np, this QAOA is not same as simulated annealing. Now, what are the results that we know? If you remember, or if you don't, just recall it right now. This GW algorithm for max cut gives a cut of size 0.858. For 3 regular graphs, interestingly, what result we have is for 3 regular graphs. 3 regular graph means each and every vertex has 3 edges attached to it. Or in other words, each vertex has 3 neighbors. So this is called a 3 regular graph. So for 3 regular graph, if we run QAOA with p equal to 1, it gives a cut size of 0.692. Now you can think here that this is not as good as this. This is 8/58, this is 692. But think of it in this way. This is for p equal to 1, a single iteration, whereas GW algorithm requires order of n cube. So if you are talking about a 100 qubit graph, graph with 100 vertices, then for GW algorithm to attain this cut size, you require a time which is proportional to 100 cube. And here I am saying that you can reach this cut by just a single iteration. So this is the power of quantum computing that you see. And the promise is that as you increase P, this approximation ratio will not decrease, but rather it will start to increase as you increase P. And there is one more result. There is one thing that I left out earlier, is that for these near-term devices, the number of qubits should be small. That is something we said. But three-regular graph, it can be a three-regular graph with 100 vertices. So this is what has been shown in the paper, that if you have a three-regular graph, irrespective of the number of vertices, you can run this algorithm on a quantum computer with only 15 vertices. We'll not go into the detail of that, but it is a result. You can do that with only 15 vertices. So this algorithm actually satisfies all the constraints of these near-term devices, and still it doesn't give a better result than classical algorithm, but it promises, or it rather shows the potential that as we increase P, we can get, or maybe we can even beat this GW algorithm. Now, there are some limitations as well. First, the question is, can we really beat this GW algorithm by increasing P? This result is not known. Rather, for any deregular graph, there is a result that if P is less than log n, then you cannot outperform this GW algorithm. But what happens if P is greater than log n? We don't know, because we are very happy to allow what we say is polynomial time. What is P is equal to order of n? What is P is equal to n square? We don't know. So these are all open fields that we still don't know. And there is a second limitation, that we are already thinking only of this P, the number of times you are using these iterations. But here, here we have this optimization part, right? You need to optimize beta and gamma. And as P tends to increase, the number of parameters increase. So this optimization will take up a really long time in a classical computer. So we cannot just only think in terms of P, that we are saying that a single iteration or two iterations, but we also have to take into consideration that the optimization can take up a long time. How long? So here is a result by Intel Labs actually. So they showed that this red line is for P equal to 4 and this green line is for P equal to 8. And here is the time that will be required as the number of qubits vary. So number of qubits, they have varied from 0 to 400, and this is the time requirement. And why does this time requirement grow so much? It grows so much only because of this optimization part, which is done in a classical computer. And this blue here, this blue line, on the other hand, is the classical SAT solver that is used by many researchers now who are working on optimization problems. So you see, this SAT solver requires a much less time than this QAOA. And again, the only reason for that, this is again for P equal to 8, P equal to 4. These are very small values of P. But the optimization part itself, it takes up a huge time. And that is a huge limitation of QAOA. But obviously there are some solutions that have been proposed here. The first is Farhi. Farhi actually came up with this QAOA algorithm. So he said that you take a small graph, you fix the number of iterations P, you take a small graph, you do an exhaustive search over that for the best parameters. When n is small, you can see here, when n is small, the time requirement is small actually. So when n is small, you can exhaustively search for the parameters, and then you store these parameters, and even for higher n, you use these parameters only. Because as you start growing for higher n, this time requirement for optimization grows. So you don't have to give that much time. You do that once, store it, use it for later. So that actually is a very nice solution, but it has some drawbacks, is that for higher n, it is possible that the performance of the algorithm is hampered because of this. Because maybe there were some other parameter values which would have given you a better solution, but you are using some other parameter values. So the performance of the algorithm can be hampered. However, Farhi has used some numerical simulations and shown that in those numerical simulations, there is a performance degradation using this technique, but it is not that, it is not humongous. It is maybe acceptable. The second solution, of course, machine learning is everywhere. So we should have some machine learning based solution. So the idea is, again, for p equal to 1, you exhaustively search the parameter values. So for p equal to 1, there are only two parameters, one beta, one gamma. You exhaustively search for the parameter values. And then using this value, you train a machine that will be able to guess the values of the parameters for higher p's. And starting with those parameters, you try to tune them such that you reach the optimal values of the parameter. So using this technique, this paper has shown that on average, 45% around reduction is achievable. In fact, they have found some instances where the time requirement has reduced by nearly 65%. So these are some solutions, and there are lots of open questions. If you have actually paid attention here, all the papers, most of the papers that I am citing are from 2019 and even from 2020. So this is one of the very, very recent field that is people are working on. And there are lots of open questions, and in fact, maybe there are more unknown problems than known problems. For example, how does the approximation ratio vary with increasing p? This is a very interesting problem. And all this time I have been talking about three regular graph. So what does happen? What happens when you have some other form of graphs, some general graphs? You can have some social network type of graphs. What happens there? We don't know. And finally, I have been only talking on max-cut problem. Can we use it on other combinatorial optimization problems? And this has been slightly studied by Stuart Hadfield. He's in NASA right now. But he has developed the icing formulations for many other NP-config problems, but the performance guarantee is still not known. So these are many open questions that are here. Lots of research areas, lots of open problems, and these algorithms are some of them. This QAOA for combinatorial optimization and these similar type of variation algorithms for quantum chemistry. These are two hot topics right now that are being pursued, that are expected that using these near-term noisy devices, we can still do something better than classical computers using this type of algorithms and on. So there are many problems that I am trying to learn, you can try to learn, and you can try to work on. I am also trying to work on. So that's all. Thank you. And if you want to have some questions, suggestions, comments, feel free to drop a mail or you can shout out in Twitter. And so that's all. Thanks for listening.
Thank you, Ritojit, for such an interesting talk. We'll have a short question-answer session. So I'm just reading out the questions. So the first question is from Alokparna Choudhury. So she is asking, in order to apply in any dynamic optimization problem, what gate is more useful for updating the qubit? Is there any disadvantage which we may face if we use the rotation gate in this problem?
Well, so for dynamical optimization problems, to be honest, I don't know. I don't think there is any paper that looks into that. I don't know of any paper. There may be, but I don't know. And secondly, talking about this rotation gates here, QAOA uses a particular form of ansatz that we showed, this UHP and UHP. It uses a particular form of ansatz, but this same problem you can approach using other types too, that is called the same variational approach, but variational quantum eigensolver, VQE, where you can actually prepare this ansatz in different ways. So it is actually not known whether you can have some other ansatz, maybe rotational gates or something other that can give you even a better approximation ratio. So yeah, it can be possible.
Okay, the second question is from Deboshmita Bhomik. So she is asking that what situation happens if T varies faster? Reference slide 29.
Okay, so if T varies faster, actually, this is an adiabatic process, and if T varies faster, then this algorithm does not guarantee. It says that the T should be proportional to 1 over that G mean square. If you are not following this time scale and if you are doing it faster, there is no guarantee that even after allowing that much time, your system will settle in the ground state of your problem Hamiltonian. You may have some different answers. So the theorem actually does not hold if you don't follow that T.
Okay, the third question is from Jay Midda. He is asking, is there any quantum algorithm which can be replicated in classical computers?
Okay. Look, this is an interesting question. I would say most of these quantum algorithms can be replicated in a classical computer. Even if you see, just let me go back here. Okay, this solution that I am showing you here, this is the output. This I have done in a classical computer. This is a simulation. You can even do Shor algorithm on a classical computer. Any quantum algorithm, you can write a program. There are many simulators now. Qiskit is one that Shojanno will show in the next talk. Qiskit is one of them, and there are others as well. You can definitely run this in classical computer, but then the speed up that you obtain for this superposition, I haven't talked of entanglement, but these type of things, these are lost, one thing. And the second thing is, if you start increasing the number of qubits, then you cannot do this simulation anymore. To the best I know, Atos has a classical computer that can simulate up to 41 qubits. And to simulate up to 41 qubits, you require a time of order of 2 to the power 41. Our natural computers will not do this, and you need a supercomputer. But even then, beyond a very small number of qubits, you cannot simulate it. But yeah, there is no reason why you cannot do that.
The next question is, can all NP-conflict problems be converted to quantum form using Ising model? Is there a strategy we can universally use?
The question got cut up.
Yeah, can all NP-complete problems be converted to quantum form using Ising model? Is there a strategy which we can use universally?
Sorry, the question is getting cut up a lot.
Okay, the question is that can we convert all NP-complete problems to quantum form using the Ising model?
Okay, this is because the voice is.
Hello, I am audible now? Am I audible now? Hello? Hello?
I think Ritojit's internet connection has dropped.
Okay, there has been an issue with Ritojit's internet connection.
Yeah, I have written the question in chat. If he comes online, he'll be able to read it up.
Okay, so we'll resume this session again once Ritojit joins up. So we'll move on to our next session. So the next session, which is the second part of our work, is on realization and implementation of quantum algorithms in a quantum circuit on IBM Qiskit by Shojanno Roy. So Shojanno Roy graduated from Netaji Subhash Engineering College in Computer Science and Engineering. He was an ex-Google DSC lead won second runner in 2017 ACM BTech Project Award and TCS Enginex 2018. His research interests are machine learning, deep learning, social networks, and quantum computing. He has published 6 research papers in these fields. I request Shoujanno to begin his talk. We'll resume Ritoji's session once Shoujanno's talk finishes. So Shoujanno, can you please begin your session?
Yeah, am I audible and is my slide visible?
You are audible, but your slide is still not visible.
Oh, I have to present. I'm sorry. I have to present. So, no. Yeah, I hope now it is visible.
Yeah, it's coming up.
Awesome.
Yeah, it's visible now.
Okay. So, hello people. Good afternoon, good morning, good evening, wherever you are right now. It will be uploaded to YouTube and you'll be able to share, see it in your time accordingly. So, all kind of salutations included. I am Shoujanno and I lead a small group called Q Kolkata, who Q Kolkata is a group of quantum enthusiasts and researchers and also experts that spreads the knowledge of quantum computing to the beginners as well as people who have already started, and influences people to come into this field as this quantum computing, the field is growing and is very old. It's like started from 1920s, 1930s, the entire quantum physics. So right now we have reached a level of abstraction where even if you don't have the entire knowledge of quantum mechanics or quantum physics or the deep maths, you can still do some work and you can still code up quantum algorithms. So we'll talk about this, and my talk is based on realization and implementation of a quantum algorithm in quantum circuit on Qiskit. So if you don't know, Qiskit is a framework on Python by IBM, and it allows you to simulate quantum computers in your local device. Or if you want to run this, run your code on real quantum computers, IBM allows you to do that as well. They have got 3 to 4 quantum computers in their data house, and they give you access to those computers, and you can run your code actually in those computers, but it takes a little bit of time and it gives you a good result. So without further delay, let's start the session. So first thing I want to talk about, the first thing is let's put on the thinking cap of Sir Richard Feynman and let's start today's session. So first of all, what is computing? We need to understand, before we get into quantum computers, we need to understand the bare bones of computers. So the bare bones of computers starts with the information that you want to process. So the information is the first part. The second thing comes is the system. So you put information into the system, and the third thing is the algorithm. Now the system is run by the algorithm. So the information comes into the system, and there is algorithm that runs the information, that does something with the information, and finally you have the result. Now you can invent any kind of computing, be it a classical computer, be it a computer made up of photons, be it a quantum computer, be it a DNA computer, but these 4 pillars won't change. It will stay put, and this is based on the Turing machine, if you know what it is. So these are the 4 pillars. Now, what is a classical computer at a bit level? Now, at a bit level, if you see, the classical computers are classical bits or voltages that run on classical wire, that is stored in classical registers, and they run on classical wires and through classical gates. So if you see a classical computer at a very fundamental bit level, it is these 4 things that a 0 is represented by low voltage and 1 is represented by high voltage. And they are stored in a register made up of either capacitor or flip-flop or anything as transistor maybe. And they run on wires, that is normal wires that we have, but in the CPU, the wires are much smaller, much well-defined, and they have very less resistance, but actually they are principally wires. And they are the entire thing run on gates. Now gates as the Boolean gates like AND gate, OR gate, NOT gate, XOR gate, we have different kinds of gates. So this is classical computers at a bit level. Now what are quantum computers at bit level or qubit level? Now, as Ritojit has already shared about what are qubits and all, so I will go a little bit deep, but not now. So let's see what is quantum computers at a qubit level. Now, a qubit is a quantum bit, and they are stored in a quantum register, and it runs on quantum wires and through quantum gates. Now you may think that I have just put quantum in front of all the words instead of classical from my previous slide, but this is the actual thing that happens. And don't worry, we'll go deep into this, and you will have a clear understanding by the end of my talk of what am I talking about right now. So let's move forward and see that classical computers that we use today, and that includes the laptops, the telephones, the mobile phones, the smartphones that we have inside our pockets. These are not developed in 10 or 20 years. This has been constant research and development, engineering challenges, technological development of several decades. And it's hard to say decades. It may be a century's work, the current mobile phones that you have inside your pocket. So it has started from those transistors, it has started from those vacuum tubes and have grown and grown and grown, and levels of abstractions were there, and finally you have these apps that are so engaging, that are so informative, that run on these screens. So we will see what are those abstraction levels. First, these are bits that run inside the wires, and then they have transistors that that has the bits in it, or controls the bit through gates. And this entire work is controlled by Boolean algebra. And then Boolean algebra, on top of Boolean algebra is machine level code, or a machine language. Then we have assembly language. And then we have human level languages like human level codes. And then you have multiple layers of abstraction. And finally, you get the current computing realm. So all the apps that you use are nothing but layers and layers of abstraction that is a result of century of research and development. But what about the quantum computers? Are we still on the same page with the classical computers? The answer is no. The quantum computing is still in the baby stage of gate-based computing, right? So if you go back and see, we invented transistors and we invented gates around in 1950s, and then we made silicon chips or integrated circuits that in a single chip we could put many transistors, and those integrated circuits size grew, and the number of transistors inside the integrated circuit, the numbers grew. So we are still in that stage where there are gates and we are pushing in bits and we are getting the results. So a lot is left to do, and we still don't know what will we get out of this levels of abstraction on a quantum computer. Right? The levels of abstraction on a classical computer has been a game changer and has transformed the entire world as we know it. Now we are not sure what abstractions of quantum computers will do. So there are let's see how the current quantum computers look like. So this is what it looks like. I'll use the pointer so this is the quantum chip actually, that is the heart of the system, and it you may think how many bits or how many qubits do they have. So I'll give you a rough idea. Controlling and stabilizing and stopping the interference of like 5 or 6 qubits is a huge deal for today. But there are companies that are working towards greater number of qubits, 19 qubits or 23 qubit system. But we are a long way from there. So this is the processor that holds the qubits and the registers. And this processor is mounted at the end of this chandelier. So this is the golden chandelier, and this is from IBM. This entire system is just for cooling and cooling the system, cooling the chip to 0.015 Kelvin. That is almost equals to 1 millikelvin. And that is the temperature at which the quantum phenomena acts on the quantum chip, so that you can use them to do the quantum computation. And this entire chandelier is put inside a cover like this, and it's frozen. And it also stops interference like radio waves and all kinds of electromagnetic waves and noises so that the qubits won't get destroyed. So the qubits are very fragile and it interferes a lot, but that's how we do it right now. And this is a gate-based computing mechanism, and we will see what others are there. So right now, what players are there in the market? So the current market of quantum computing has Google. As you have heard the news of Google cracking a quantum supremacy code in the past, and I think in 2019. And then we have the D-Wave. Now, D-Wave system uses adiabatic quantum computing for their system, and this is the only company in the world that is selling quantum computers right now to its customer. And there is IBM that we already saw and we will see. And recently Honeywell came up with a quantum computing system. So these are the present big players who are working, and there are many customers of them who are pitching them money and buying system and also helping them to research and develop more and more quantum computers. So what can you do right now? Now, we have already explored the field, how it is, and saw what not about the field. But what can you as a student or as a researcher can do right now? First thing you can do is stop worrying about the hardwares, because the hardwares are way expensive and they are way complicated for us to design from scratch, and it's pretty hard. So what you can do is stop worrying about the hardwares, and I'll tell you why. Also, you can stop worrying about the complex maths behind, and this is also, we will know why. And the next thing is you can think about the abstractions that can be built over the current quantum computers, so that it helps us in the future and enhance, uses the power of quantum mechanics to solve problems. And the fourth thing you can do, you can look for resources to learn this subject. There are millions of resources. Millions is a big word. I'll say thousands of resources in around the internet with good courses, good lectures, good papers, books all around. You can just search up and read up. And if you're not afraid of mathematics, I'll encourage you to go deep into the mathematics, because it's beautiful once you know the maths. And I'll quote a professor of mine who said this, that English is not a subject that can, no natural language, not only English, no natural language has been invented to describe the quantum phenomena correctly. Like the entire quantum mechanics, you don't have enough words, enough expressions, enough phrases to describe what is happening in the quantum realm. The only language that can describe this quantum realm properly to bit is mathematics. So if you are not afraid of maths, I'll encourage you again to go deep into the maths. It's beautiful once you understand. The next thing, remember that exploiting the quantum mechanics for computation has many advantages to the present way of computing, as we will see how quantum computers exploit this and reduces the time of classical algorithms in a huge way. And lastly, pay attention to the rest of the lectures. So yeah, this is what you can do right now. And let's move on. Now, types of quantum computing. Right now we have adiabatic quantum computing that uses quantum adiabatic phenomena to calculate its results. Then we have gate-based quantum computing, and most of the companies except D-Wave are using gate-based quantum computing for their computers. And lastly, we have universal quantum computers. Now, universal quantum computers are the holy grail of quantum computers, because once we make a proper 100% universal quantum computer, that will be the day of change. So qubits, yes, let's talk about qubits now. Now, qubits are bits that is one, that may be zero, or that may be a combination of 1 and 0 at the same time. Now, what do I mean by this? Let's see what qubits are. Let me tell you about, this is the vectorial representation that I'm about to show you. Now, the qubit 0, if you see the qubit 0 is kind of represented by this. And I'll confirm if my screen is visible where I'm writing to the... Anybody can, in the chat, can confirm? Anybody can confirm whether my screen is visible where I'm writing?
Yeah, the screen is visible. Shojan, you can continue.
Awesome. Cool. So, and the qubit 1 is represented in vectorial form as, okay, so I'll write it here as 0 and 1. So this is how you represent the qubits in the vectorial representation. And the thing that I said that they can be 0 and 1 at the same time is by superposition, and we will see that in upcoming slides. So, okay. So then we have the bracket representation. Now, this bracket representation has been invented by Paul Dirac, and yesterday was his birthday, and he was one of the founding fathers of the quantum mechanics. So we will see what bracket representation is. It's very easy. Like if you want to represent 0 qubit, then you write something alpha of 0, and you write with beta of 0, beta of 1. And this alpha and beta are nothing but the probabilities that this qubit is 0 and 1, and it is normalized. Like if you do alpha square plus beta square, you will end up with 1. So this is 0 qubit, and then you can represent the 1 qubit as well. It goes the same way, alpha 0 plus beta 1. So that's the bracket representation. And then one more thing you have is the visualization. How can you visualize qubit? Now, block sphere visualization is one of the best visualization you have for qubits, and it looks like this. And Ritojit has already talked about this in his talk. So I won't go deeper into this. And lastly, you have measuring qubits. Now, as I told you before, the qubits are, when the qubits are in superposition, when they are perfectly 1 or 0, we don't have any problem with that. But when the qubits are in superposition, then measuring them, that measuring means when we see or when we try to poke into the information and see what state they are in, then they lose the state of superposition and collapses in either 1 or 0 state. So everything we'll have a practical demonstration. Let's go forward. So what are the so now we saw how can we represent qubit, and we can write qubit in paper, or we can visualize qubit in a block sphere, or how measurement of the qubit affects the qubit. So how actually physically, how do you make a qubit? Right, you may think what thing do you need, what hardware do you need to physically make a qubit, and that will be answered here. Like you may use atoms, neutral atoms, to make qubits, or you may use trapped ions to make qubits. Now, trapped ions are, you have magnetic field and you put ions in those field, and the ions get trapped, and you can use those as qubits. Then you have color centers, or nitrogen vacancy centers in diamonds. They can be also used as qubits. And then you have electron spins. Now, electron spin is also a very good candidate for representing qubit. When you have a positive spin, you may tell that as 1. If you have a negative spin, you may tell that qubit as 0, or vice versa. But electron spin is also a good candidate for physically representing a qubit. And then you have superconducting qubits. Now, superconducting qubits are a result of exchange of charge, phase, and flux. And then you have nuclear magnetic resonance qubits, and optical qubits by photons, and lastly, topological qubits. Now, here, this is a very big information slide, and I just want you to know that though there are many ways of representing qubit, but the underlying theory and underlying maths is same for all. They do not change. The underlying mathematics do not change, and the most famous out of this is the superconducting qubit, and it is being used by Google and IBM for their work. The next famous qubit you can say is electron spin qubit, and the next famous is ion trapped qubit, and the next famous is optical qubits. So they have their own share of advantages and disadvantages, but this is what it is. So let's move on. And see what are quantum gates. Now, why am I moving so fast? Because the topic of the talk is discussing an algorithm, and we'll be discussing an algorithm. But to discuss that algorithm, we need some prerequisites. So many of you may be watching the video with a strong background of quantum physics or maybe quantum computing, but many of you who are watching may be newcomers. So this is the fastest or the best way I could take away my talk. So let's talk about quantum gates. Now, these quantum gates are single qubit gates. Like in classical, we have just one single qubit gate, and that is the NOT gate. And rest of the gates are either 2 plus n gates, like AND gate, OR gate, and then you have NAND gate, all those other gates. But in quantum computers, we have many single qubit gates, and the first gate is the X gate, and X gate is a NOT gate, which flips the qubit in its state. So if you have a 0 1 and you apply the NOT gate, it changes to 1 0, and vice versa. And you can okay, I'll tell this I'll tell this later. So you have a Y gate as well, and you have a Z gate, and these three gates are known as Pauli gates from Wolfgang Pauli, or you may have read Pauli exclusion principle. So he's the same Pauli who worked on this, and these gates are nothing but rotational gates on this specific axis on the block sphere. So X gate is a gate which, if this is the sphere, X gate, what it does is it rotates the qubit on the X axis, Y gate rotates the qubit on Y axis, and Z gate rotates the qubit on Z axis. So these are also known as rotational gates or Pauli gates. The next gate we have is a Hadamard gate. Now Hadamard gate is a pretty amazing gate. What it does is it brings a qubit from 0 or 1 to superposition. And we'll see how. So Hadamard gate is a pretty awesome gate. And then we have the R5 gate. Now this is the first parameterized gate. All the 4 gates that we have discussed here, X, Y, Z, and Hadamard, are non-parameterized gate, but that means they do not depend on some other input you give. They solely depend on the qubits. Whereas this R5 gate is a parameterized gate, and it is dependent on the value phi that you put in, and it changes on the basis of that. And then you have the identity gate. You have heard about identity matrix, and this is the same thing. And it does nothing to the qubit. It is just, it leaves it as it is. And then we have the S gate and the S dagger gate, the T gate and the T dagger gate, and the universal gate. Now S gate and T gate are non-parameterized gate, but U gate is a universal gate which can simulate, which can act as all the above gates. So this is the chart where you see these are the single qubit gates, quantum gates, and multi-qubit gates. Now after this, let's talk about the qubits that use the gate that uses multi-qubits. So first thing is the C0 gate. Now C0 gate is also a pretty amazing gate. It's a 4-dimensional gate. So there is 4 columns and rows. And why is it amazing? Because it helps it helps the qubits to go into the state of entanglement, and we will see that as well. So I am already putting so much asterisks that we will see later, but we'll definitely see these things. We have time. So, and the next gate is Toffoli gate. So this is a 3-qubit gate. C0 gate is a 2-qubit gate, and Toffoli gate is a 3-qubit gate. So these are all the gates that are available. There are many other gates that I did not discuss, but we will see. Yeah, definitely. I promise we will see. So quantum speed up. Now we have talked about so much in this so less time. Now let's slow down and see what these quantum computers actually help us to do. So what does it help us to do? First, it decreases time of operation, or it decreases time of complexity, and sometimes it decreases the space complexity as well. So if you see, if you want to check a function, if it is constant or balanced, Now, what do you mean by constant or balanced? Suppose you have a black box and you put in something and it outputs every time, it is outputting the same thing, no matter what you input, then it is a constant function. But if you put in, it's the same black box, and if you're putting in something and it is outputting different thing, then it is known as balanced. That is how I can explain you the constant or balanced function superficially, but if you go inside it, it's much complex. So that is the superficial or analogical definition you may have. For a classical computer, it takes roughly O to the power n times, but if you actually see it, so O to the power n minus 1 plus 1, so n minus 1 plus 1. So it takes this amount of time because you have to check all possible combinations of input and check whether the output is the same or different or constant or balanced respectively. But in quantum computers, you can do this in just one shot. Yes, just one input and you can tell whether the function is constant or balanced. So yeah, that is how quantum computers help us. The second thing, there are many algorithms like this. I have put my top 3 favorite, and one of that I did not put. I'll talk about that. So the second thing is searching for a bitwise multiplier. So for a classical computer, again, I'll explain you this analogically and superficially, but don't go into my words. So what is bitwise multiplier? Suppose you have, again, black box function, and you put inside a stream of bits and you get an output, and I should show this here. It will be, so if you have a black box and you put a stream of bits, right? You put a stream of bits and you get something out, and this output is nothing but suppose you're entering the stream of bits x. This is a function f of x, and you are receiving something s dot x. This is the output. So you need to figure out s. So for a classical computer, this takes about O to the O n times. Why? Because you need to put in entire stream of bits and then you can see the answer. But again, a quantum computer just need one shot to solve this problem. So let's see another example of this. It's getting better each time. So checking of mapping, whether function is 1-to-1 map or 2-to-1 map. So if you remember, 1-to-1 map is, I'll just briefly and very quickly say what is 1-to-1 mapping and what is 2-to-1 mapping. So if we have a set like this, A and B, and let me change the color. So 1-to-1 mapping is something like this, where, and let's say A, B. So this is 1-to-1 mapping, and let me quickly say, so 2-to-1. So two things can go at one. So this is 2-to-1 mapping. So if you need to check a function, whether it is 1-to-1 or 2-to-1, in a classical computer, it needs around, again, O to the power n times, because you need to check all the possible combinations of the input. But again, a classical computer drops the bomb and it solves it in linear time, O n time. So these are few of those algorithms. I'll tell you. The first algorithm that I have stated here is Dwight-Joshua algorithm. You can Google it up. The second algorithm that I told you is Bernstein-Vazirani algorithm. And the third algorithm that we have talked about here is Simon's algorithm. So these three algorithms, and there's another algorithm called Shor's algorithm, and that is my personal favorite algorithm that exploits the quantum physics out of the universe. So yeah, this is the quantum speedup that you can achieve using a quantum computer, and here you will lose if you have a classical computer. So enough of things inside our brain. Let's take a detour and calm down and just see what Qiskit framework is all about. So here I have already opened the Qiskit framework. So you can go to quantum-experience.ibm.com and this thing will open up. So this is the dashboard. I can take you to the dashboard. So this is the dashboard. Yep. So this is the primary homepage that you will see. Okay. So, yeah. So this is the primary page that you will see. And what I have already opened is the circuit composer. Now they have recently revamped their circuit composer. It was way less informative before, but now it's way more informative. And I'll explain you what is here. Here is the main menu bar where, okay. I think I have a technical issue here. I'll just be back.
There seems to be a disconnection or an issue. Please have patience, and we will be back as soon as Sojourner is able to connect with us again.
Yep. I think I'm back. Am I back?
Yeah, visible.
Yep. Yes. So this is the entire circuit composer. Now this is the menu. This is the folder where your circuit stay. This is the demo circuit. That's the name. These all are gates that are available right in front of you. And this is the circuit. These are the qubits that they have defaultly give you. And this is the classical qubit, because once you measure the quantum qubit, you need to put that inside a classical qubit so that the qubit stays as it was while measuring, and it does not get interfered by noise and interference. And this is the state vector representation, and this is the Q sphere or 3-dimensional block sphere representation. And okay, let's do something. So here there are 3 qubits. I just want here 2 qubits. So I'll delete these 2 qubits here from, and let there be only 1 qubit. And we will see how the X gate affects it. So I'll bring a X. This is the X gate, as you can see. And as I put the X gate, you see the vector flipped. So it was in the 0 state and it flipped to the 1 state. Now you can rotate it and see. Similarly, if I don't want this gate, if I control Z, and if I want to check Y gate, yeah, it does the same thing. Now let's do something better. Let's entangle 2 qubits, and for that we will need 2 registers. So we will go to manage registers, and we will increase the number of quantum registers too. And you see the classical registers, it gets, if you click this, it will automatically synchronize with the number of quantum registers. So I'll save this, and we'll have 2 quantum registers and 2 classical registers. And I won't go deep into how entanglement works. I'll just show you the circuit. So first you need to put a Hadamard gate to make this first qubit in superposition. See, when you put a Hadamard gate, the first qubit gives 0.707 amplitude of both, and so this is what Hadamard gate does. And then you have to put a C0 gate such as this, and then you will see you just have 2 qubits, both in the state of 0, 0 and 1, 1. So this is an entangled state where both qubits are in the either 0, 0 state or 1, 1 state with 0.5 probability, and you can see the phase angle as here. And there are many other things you can do. I can show you. You can just put another Hadamard gate to see the. Okay, let's undo it. Let's remove the. You can put another Hadamard gate out here, and you can see how superposition works. Right? It's really amazing that IBM did this, and it's open for all to check. You can log in right now and play with it, put whatever gates you want, and see what output it gives. So it's pretty amazing. And also here is the code part that is read only, and this gives you the code where you can copy and paste it to the notebooks. Yeah, I did not talk about the notebooks. They already have a quantum lab which is filled up of Jupyter notebooks. So here you can put a new notebook and start coding in Python, and that gives you an edge over the limitations that the circuits have. So we will do that. But again, let's get back to the lecture. So enough of detour. Now, this is what we prepared for. Now I think I'll put down the camera. I'll put down the camera, and because I have to write a lot, and I'll clear the page. Yep. So yes, the search algorithm. Now, if you have taken a computer science or computer engineering class anywhere in your academic career, you must have studied something called a search algorithm and a sort algorithm. Now, leaving the sort algorithm aside, we'll talk about the search algorithm. Now, we know that if there is an unstructured or unsorted database, then we will have, if you do a linear search, it takes O(n) time. You have to check all the numbers for the search number, and in worst case, you won't find the number in the list, and that will result in O(n) times. But if the data set or database is sorted, and you can use an algorithm called binary search that we have also known for a while, and that does this search in O log n times. But the only disadvantage is that you need a sorted database for this. So what can we do? And for both these algorithms, we need O(n) space to store the searchable database. So how does a quantum computer helps us to achieve fasten this? So there was a man named Love Grover. He invented something called Grover's algorithm, and he did this. You can search a database that you can store in O log n space and search the database in O root n times. So this is pretty good speed up and pretty good conservation of space. And this is the algorithm that we will see today in details. So let's jump, and first let me state the algorithm for babies, right? So first thing, you need to convert the database into superposition. Now, what do I mean by superposition? We have already seen if you have 4 searchable parameters, then superposition, what superposition does is brings those 4 parameters in a level that each of the searchable parameters or each of the searchable value is equal probable to come out. So that is what superficial definition for superposition is. And then what you have to do is you have to make a function that outputs 1 for the search term and 0 otherwise. So if you have a term that you are searching for, suppose you in a list of 1 to 10, you are searching for 6. Just an example, in a list of 1 to 10, you are searching for number 6. Now, the function f of x, what it does is you put fx of any number that will give you 0, but if you put f of 6, that will give you 1. So this, you need to make a function like this, and then you need an oracle. You need to design an oracle that changes the phase of the search term. Now, big words are here: oracle and phase and change, maybe. So, an oracle is you can think an oracle is a device that if you put something, it outputs something. It's simply a kind of black box. But if you can define the oracle, it is no more a black box. So you need to change the phase of the search term. It means that again, if you're searching, it will invert the phase for the number 6. Now, inversion of phase, we will see that in a while. Then what you need to do, you need an amplitude amplification program that increases the amplitude of the search term. Again, let's go back to our previous example of searching 6 in a list of 1 to 10. Now, what happens is, I'll show you briefly what happens. Is suppose you have all the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, it's better if I write down the numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Awesome. Now, what the first function or the oracle does is, oracle takes the 6 and inverts the function. So we can think of as takes the 6 and it inverts the function. And what amplitude amplification does is, it increases the amplitude of the number 6. Now it may seem a little problematic and vague to you, but I'm sure after the end of the discussion of the algorithm, you'll be pretty clear about it. So we have done the amplitude amplification. Then you have to repeat this over and over, right? Because first, suppose I have exaggerated the amount of amplification in the first trial. So actually it happens a little bit like this. Then you again have to invert it. Then again you have to amplify it. Then again you have to invert it. Then again you have to amplify it, and such. And then when you now all the states are in superposition, means they are equal likely to be collapsed into if you measure the this state. But when you do this multiple times, this probability, the number 6 probability, increases so much that when it collapses, you get a reading of number 6 much bigger than the other superposition state. So this is a analogical or a superficial example. And when you measure the superposition state and you have your such number. Now, two things that may worry you. What if I give 2 or 3 such parameters? It works simply fine. If you have 2 or 3 parameters, suppose you are searching for number 8 as well. So it does the same thing in the parallelly. It will increase number 6 as well and number 8 as well. Again, invert, invert, increase, invert, increase. And it increases the probability of collapsion. So this is what basic Grover algorithm does. Now let's switch on. Okay, let's go to the Grover's algorithm for Avengers. Yeah. So now we are diving deep into the Grover's algorithm. Let's clear the page. So yep. Now, first we need an unstructured data set. So let me change the color here. And so suppose you want to search n numbers, and so let's make it 2 to the power n. Now n is the number of items that you are searching, and we should represent it 2 to the power n. For the limitations of the time of the talk, we will take the n to be 4, and so that we can represent it 2 to the power 2. Okay. 2 to the power 2. Now, if you have 4 numbers, then we need to binary encode these 4 numbers. Suppose we want these 4 numbers to be, let's create the list. So we want these 4 numbers to be 0, 1, 2, and 3. Now, if 0, 1, 2, and 3 are there, we need to binary encode all these numbers. So let's binary encode the numbers. So 0 to be 0, 0. We know this, right? We have done plenty of Boolean algebra in our 0 and 1, 1. So binary encoding is done. Now this binary encoding helps us to get into the state of superposition. So 2 steps are done. Now we need to design a function that we talked about that returns 1 for the searchable items and returns 0 for the non-searchable items. Now suppose our searchable item that we want to search is 2, and we will mark it with a box and we'll write W. W stands for the winner or the searchable item that we are trying to search, and the rest of the numbers, let's mark them X. So X are the items that we don't want to, that are not searched, we don't want to search. So a function f, what it does is, if f is X, you will get an output 0, and if f is W, you get output 1. Awesome. So after you design this function, then you need to put this thing into superposition. You need to put the numbers into superposition. Now, as they are already converted into binary, it's very easy to put this number into superposition. How? By just putting 2 Hadamard gates. If I draw the circuit here, if I briefly draw the circuit, we'll be drawing the circuit in detail. But if we draw the circuit, see, as there are 2 bits in every number, so we just need 2 quantum bit to represent all these phone numbers. Sorry, it will be 1. I'll correct it. So you just need 2 quantum bits to represent the 4 numbers. And if you put a Hadamard gate in front of 2 qubits, what it does is it brings these 2 qubits in superposition state. Now, what do I mean by superposition state? I'll just write it down. So the superposition states will look like 0, 0, plus 1, 1, almost, right? 0, 0, 0, 1, 1, 0, 1, 1. So when they are in superposition, they'll be equally probable when if you measure these 2 qubits, there is an equal chance that this will come out. So if there are 4 numbers, it's almost equals to 0.25. The probability of showing up 25 and 0.25, 0.25 for them to show up. Now our job will be to increase the number 2's chance, because we are searching for number 2. So for that, we need to design the oracle. Remember, we talked about the oracle. So we need to design the oracle so that it flips the stage of number 2. So I'll again box the number 2 here so that we stay on the same page. We are searching for number 2. And we need an oracle. So let's design the oracle. I'll change the color. Hold on. Yeah. So the oracle UF will look like this. That if, the UF of X will look like this. That if you put F of X of X. So it uses the function that we have already declared here and inverts the phase of the searched item. So I'll give you an example. So if you have UF of 1 maybe, so 1 is 0, 1. So I'll just write 1. Then it'll give you F of X will be 0 for 1. If F of 1 will be 0, so minus 1 to the power 0 of 1 will be just 1. And if you have a searchable parameter, suppose we have the number 2 we talked about. The number 2. Again, 2 is nothing but 1, 0. I'll just write 2 here for simplicity. So minus 1. And F of X for 2. So F of 2 will give you 1. So it will give you 1. And of X, of 2 again. So you see, it is minus 1 or minus of 2. So to generalize it, I'll generalize it here. So this oracle again does what it does is F of X is equals to X and U of F of W is minus. So this is the result of this oracle. So I hope we are clear with the first part of the oracle designing, and there is nothing more to it. Obviously there is more to it. You can go deeper into the designing of this oracle, designing of the function, and learn more about it. But this is what I have designed for my talk. And now is the second part that tells you the amplitude amplification. So amplitude amplification. The first amp stands for amplitude, the second amp stands for amplification. Now remember we were searching this. So I'll write it down again. So let me write it down. And their amplitudes. So the non-searchable terms were green. So this is for number 1. Sorry, this is for number 0. And this is for number 1. The color here is just for knowing that what term we are searching for, but it does not affect the quantum computer. It's just the term we are searching for. Now you see all this, it's at around 0.25 because there are 4 numbers. There is equal probability of these numbers of showing up if you measure. Now we need to apply the amplitude amplification function and see what we can do to search this number in one shot. So before we go in, we have already talked about putting this number into superposition. Now, as these numbers already are in superposition, that state, we can represent it by the state S, where S is nothing but 1 upon n. Again, n is the number of searching parameters, summation of n minus 1 x0 to n minus 1 of x. So this is what the superposition state in an equation looks like. Now, again, we cannot measure the superposition, but if we measure the superposition, the state will collapse in either 0 or 1 or 2 or 3. So we have to refrain us from measuring. And then we have to understand that the S, the superposition state S and the superposition state W are nothing but vectors in the vector space or complex space of Cn. Yes, so they are vectors and they are not perpendicular. They are almost perpendicular but not perpendicular. So let's draw how it may look. Let's use the red. Okay, let's use the red, no problem. So this is the W in the vector space, and I'll not exaggerate, but this is the S state. So remember, S is the superposition state of all the qubits, and W is just the searchable item that we are searching. So this is what it is. Now we need to introduce a state S dash which is perpendicular to W. So let's introduce a state which is S dash. I'll use a different color for this. So the dash went off, so I'll do another dash. Yes. So we introduced a S dash state which is in the same complex plane and which is perpendicular to W, or the searchable item. Now, if you see this angle, and we mark this angle as theta. So theta is what? The theta is the separation of the superposition state and the S dash state that we have just declared. Now, if you see, we have a better representation of the state S, and the state S can be represented by sign of okay. Let's undo it because I went off. Yeah. So sine of theta of W plus cos theta of S dash. So this is a proper representation of S dash state, and if you pay attention and if you really are interested about the theta, then theta has a acute definition that theta is nothing but arc sine of S W. Now you may ask, what is this? This is a inner product of bracket representation, and this is also equals to SW is also equals to arc sine 1 by root n. So this is the definition. I'll encircle so that they are quite visible. So I'll encircle this in blue. Awesome. Now we have almost arranged the ingredient that was required for us to start searching. Now comes the interesting part. Okay, now I'll just put this 0.25 as we have got a representation. So this is nothing but state of 1 by root n. Okay, now we need to apply the oracle reflection. Now starts the reflection of the oracle that we have already seen. Here. So this is the oracle function. This is the oracle. I should not use the black here. I should use some other color. So let me choose a different color. Yeah. So this is the oracle definition that we saw, and this is the proper definition. Yeah. We will be using this now to reflect this. So let's reflect it in a different color. So reflection of S into S dash. So we'll see something like this, where this will also be theta. So, yep. So this is the reflection that UF causes to S on S dash. And with this, if you want to have this definition as well, let's draw it up. So that will be something like this. So we had zero, 1, 3. Now when you reflect it using the UF oracle, it reflects or put the amplitude in the negative way that here we saw with the example. It does a negative job here. It puts a negative sign in front of the searched item. So this is number 2. And as this happens, the average decreases a little bit. Before it was on the top, but now it's a little bit below. So up till here, the first part is done. Now we will concentrate on the second part, and the second part is nothing else but just doing this continuously, applying. Now we need to apply a reflection on. Let me draw this again. Let me draw this part again, because we'll be using it. So let's draw this here. So this was our S, this was our S dash, and this was our reflection that we did before. Now we need to reflect this. Let me change the color again. We need to reflect this line. We need to reflect this line on this line. So if you reflect the already reflected line on this line, we will be achieving something like this. Again, all the reflections, all the angles, all the things are exaggerated, but it happens in a very minuscule way, very tiny amount, and that's why we need to do it again and again. That I'll speak about later. So when you do this, you reach a state of where the angle is 2 theta, and you can call it, okay, I just missed the W. Just missed the W here. Yes. So what does this do? Okay, let me mark the arrows so that you can follow what comes after the other. So I'll mark the arrow. After this comes this. After this comes this. And from here we'll go again here. So what this does is it reflects again on this axis and doubles almost doubles the amount. So if I draw that again, I draw this figure again, you will see something. Okay, I hope I'm there. Yeah. So 0, there's 1, and 2 increases a lot, and there is 3. And what it does is it increases the average by a little bit. So this is what you achieve after one cycle, but that is not enough, because when you do it once, the amplitude does not increases by the amount that I have shown here. It's just again the exaggeration so that you understand, but you need to do it multiple amount of times so that it increases. So I'll give you how it increases. So the first time, suppose I'll draw it again. So first time it increases a little bit, then again you apply reverse the UF oracle, and again you apply US oracle, again you apply UF oracle, US oracle, UF oracle, US oracle, UF oracle, US oracle, and it increases. So that's how you need to repeat the steps again and again so that the amplitude increases enough so that when you collapse the state, when you measure the qubits, it gives you the answer that you are looking for. Now, how many times do you have to do this? It turns out experimentally, it has been proven that you have to do it almost the level is A, and you have to do it almost root n times. So if you do it root n times, the step of using UF and US, you have to loop it root n times almost, and that increases the amplitude far enough so that when you measure, it collapses to the expected state. So how does the circuit look for the 2-qubit example that we saw? So let's draw the circuit up. So I'll use a different color again. So you need, as we discussed, we need 2 qubits for postage to search, and we have already learned that we need 2 Hadamard gates. To put the qubits in superposition, but now here we need the oracle. Now to design the oracle, I cannot go into details because I think I have just 20 minutes left of my talk, and there is a little bit left to cover. So I'll just design the circuit, and then we'll jump to the live coding thing. So we need 2 X gates here, and these X gates are the NOT gates that we saw previously. And from there, we need, let me draw it, then I'll be explaining. So using different color. So this is a Z gate, control here. And then again, there's a bunch of X gates. And this finishes your first UF oracle. So, okay, so if I circle it, this part is UF oracle, and then you need to design the US oracle. For that, again, you need Hadamard gates. 2 Hadamard gates, and then you need 2 Z gates. So I'll use a different color for Z gates. So I'll use this. And then again, you need a Z control. So let's do that. Okay. Let's continue the qubit line. And end up with Hadamard gates again. And lastly, we measure. And measuring means we actually drop them into classical bits so that they are stored. So this part that we drew, this part is the US oracle. So this is the circuit that we use to search in a list of 4. I think I have missed one here. Yeah, oh, no. Black. Yeah. So in a list of 4, we use this circuit to search the item in root n times. So this was the rundown of the entire thing. So I'll give you another view. So we have n items. We have, suppose for example, we have taken 4 items here, 0 to 3. We need to design a function that function outputs 0 when you are searching for the not search parameter, not search item, and that outputs 1 when you are putting in the searched item. Then you need to put the states into superposition. You need to make an oracle that inverses the phase of the searched item and does nothing to the phase of the unsearched item. Then you need an amplitude amplification oracle that increases the amplitude of the searched item. So I'll leave you here, and I just pass through, and this is the circuit. So let's get back to the slides. Okay. Let's get back to the slides. So Oracle UF, we did this, then we put the database to the superposition, then we made the function that does this, and we made an oracle that inverts the phase of the searched item only. And here I think I can turn on my camera as well. So get back. Yeah. So this was the UF part, and then the second part is here, the Oracle US, that we introduced the amplitude amplification, and S is the superposition of all state, and W is the search item, and they are non-perpendicular states in a vector space of complex. That's a complex space of Cn, and introduced a perpendicular state that is S dash to W, and we apply the Oracle reflection UF on S dash, and apply the Oracle reflection of US on S, and then do step 5 and 6, root n times, and finally we measure the superposition. This is the entire rundown of your Grover's algorithm. So, okay, now let's see this in action. So I have already coded the Grover's algorithm for you, and I'll explain what is going on here. So this is the interface. This is what IBM Qiskit's Jupyter notebook looks like. Like in the previous slide, so if you open a new notebook, it helps you. It's taking a little bit of time, but I think it will be here. Yes. So it opens an empty IPy1B notebook where you can start coding, and this is entirely based on their cloud, does not use your system's resources. So this is the usual thing that Qiskit does, and it's just the functions or the headers that you need. So I have already done it for you. So this is the import part where you are importing all the necessary functions that you need. And this is the phase oracle part where you design the phase oracle. Now, and remember, we discussed the algorithm for 2 qubits, and here I'm showing you the algorithm for 3 qubits. Now, 3 qubits means we have got 8 numbers from 0 to 7, and manipulating this, we can state which number you're searching for. For here, 0 and 1 states 0, 1, 1, and that states for 3. And here 1, 2 states is 1, 1, 0, and that states for 6. And this may be a little bit confusing, but once we see the circuit, it will be very clear to you. And we will also search for 5 and 7 if you say, but I'll also search for 5. But once we have a rundown, and then I'll come here so that it's pretty clear to you. So yeah, so this is the diffuser circuit. So this is the oracle that we have discussed. Now this is the diffuser circuit. Now what we are doing is we are okay, and first of all, these are functions, and we are not executing the functions here. We'll be calling the functions into the main function. So this is the diffuser function. What it does is it takes the qubit's length and it applies the Hadamard gate here, and these are the CZ gates that I'll show you here. So this is the CZ gate, control Z gate. This is the CZ gate, control Z gate, and that is what is here. These are the CZ gates. So circuit.cz, what it does is it adds the CZ gate to your circuit. And again, here we are adding for the 3 because there are 3 qubits. This n qubit is nothing but the length of the qubits, and the length of the qubits is 3. So for 3 qubits, it will add Hadamard gate and it will add the NOT gates, and that also we add the Hadamard gate and the NOT gates. If we don't need this, I think we can turn it down. We don't need that. Yeah. And then we again add the Hadamard gates, we add CCX gates, and we add Hadamard gate to the respective qubits. And then we end up with the NOT gate and Hadamard gate. So if you see let's run the cells. So let's run the first cell. Once, let's run the second cell. Let's run the third cell. I think it is pretty clear to you right now, because these are very, very simple codes and does not require huge amount of brain power to understand. So, and this is the final function. So what we did is we put n equals to 3. That is the number of qubits we are taking is 3, and we have to use barriers, because barriers is what separates. These are the barriers that separates the parts of the circuit. So yeah, and here we are adding the edge gates to the Grover circuit. Okay, we declared the circuit here, we name it the Grover circuit, and the quantum circuit function, what it does is it calls it takes in the parameter n, that is the number of qubits we want, and returns a circuit with that number of qubits. And if you want to include a few classical bits, you can put in the number 3. It will return you a circuit with 3 quantum bits and 3 classical bits, but we don't need classical bits here. We can directly see the output for ourselves. Now we are inputting the Hadamard gate in the qubits. We are putting a barrier. Then we use the phase oracle function. We use the phase oracle function. And then we use another barrier, and then we use a diffuser function. So let me run it and let me show you. After we see the circuit, it will be very clear to you what each thing does. So this is the circuit for 3 qubits. Now I'll re-explain what was going on here. So first, this piece of code adds these 3 Hadamard gates. Right? And then this piece of code, see, firstly we have this quantum circuit returned, that is an empty circuit with just 3 qubits. But then we have applied this and we got 3 Hadamard gates, and then we added a barrier. So that's the barrier, you see. Then we called the phase oracle or Grover circuit gate, that is the first function that we used. Now here 0 and 1, the CZ gates act at 0 and 1. So it's 0 and 1. So remember, I told you this part is 3. So how is it 3? It's just we count it from the opposite way. So this is 0th qubit. I'll write it down. It will be very clear to you then. I'll try to phrase it. So oh, I lost my pen. No problem. So I'll write it here for you. So zeroth qubit, this is the 1th qubit, this is the 2nd qubit. If you are doing it, you are stating 0, 1, 1. So you read it this way. So you have 0, 1, 1, and this stands for 3. Again, if you come back here, you see this is with qubit 1 and qubit 2. As we have said here, qubit 1 and qubit 2. So what this does is, it's similar. When you do this, it means 1, 1, 0. So if you read it this way, it's nothing but number 6. So it is pretty intuitive to you. If you want to include number 5 or any other number, we'll include 5. It will simply, we need to add a CZ gate from here to here, and that will make it 1, 0, 1. That is 5. And we will be doing this. Keep this in your head. We'll be doing this. So this is the circuit, how it looks. And later, when you use the diffuser adds two Hadamard gates. The diffuser adds Hadamard gates. The diffuser adds Hadamard gate. These are the first Hadamard gates. These are the X gates. So Hadamard X. Then it adds a Hadamard gate just to the 2nd qubit. Adds a Hadamard gate just to the 2nd qubit. It adds a CCX gate to 1st, 2nd, and 3rd. 0th, 1st, and 2nd qubit. So 0th, 1st, 2nd. So you see the gate here. And then we have another Hadamard gate added to the last qubit. And we add NOT gates. We add NOT gates. And we add the last Hadamard gates remaining. So this is the UF part. This is the US part. So this is the oracle that does the reflection, and this is the oracle that does the amplification. And then we add a barrier. Sorry, in diffuser, I think we add a barrier, and then we measure all the qubits. So it's measure all. What it does is it puts a measurement unit, and there are 3 classical bits already described here that is taking in the values. So let's run the circuit. Let's simulate the circuit out here, and we will be using a QASM simulator that IBM Qiskit offers. We'll be taking 1024 shots here, and we'll be executing the result. That is our Grover circuit. We'll be using the backend, Air backend. There are 4 backends: Ignis, Air, Aquas, and I think I'll show you later. There are 4 backends. You will see it here. Yeah. Air, Aqua, Ignis, and Terra. These are the 4 backends that they offered. We'll be using Air, and we'll be calling the result function on this. And after we get the result, we will see the counts on the result, and then we'll plot the histogram. So let's do this and see what happens. Yes, this is the result that we were expecting. We found the number 3 with 0.5 probability. We found the number 6 with 0.49 probability. So this may be a little confusing to you, and you may ask why there are no other numbers. Of course, there are the numbers, but we are running this as a simulator. That's why it is giving us this. And if we run the state vector, you will see this is the number 6, 0, 1, 2, 3, 4, 5, 6, 7. Now you ask why there's no number 3. We can always get number 3 if we ran it. If you ran it, see, sometimes it will give you number 3, sometimes it will give you number 6. So 0, 1, 2, 3, or we run it again. We get number 3, we run it again. We get number 6. So it is finding number 3 and number 6 as we discussed. Now let's turn off the number 3 and number 6, and let's program in. find CZ. Remember, for 5 we need to include in a 0th qubit and the 2nd qubit. So 0th qubit and 2nd qubit. So this is what we have to do to search for 5, and we'll execute all the remaining part and see we have added the number 5th. We have added the CZ gate here and here, and we'll be running the simulator again. There's a problem. Oh, I think we are having some problem. I will need time to debug.
We can move on then because we are running out of time. So if
sure. Yeah,
helpful actually.
Yeah, this is how we do it basically. So if you are interested, I'll share the code with you, and let's get back to the thing. And I think I'm almost done with my talk. I'll leave you with a quote from Sir Richard Feynman that says, "For a successful technology, reality must take precedence over public relation, for nature cannot be fooled." And this is my handles. If you want to have some questions or some suggestions or anything, just put down here. And thank you everyone for listening to me.
Yes. Thank you, Chojanno, for such an interesting talk. As we are running out of time, we will not be holding the question answer session. Those who have questions can directly mail to seanray3000@gmail.com, and we'll be answering the questions there directly. And about feedback form and the quiz link, it will be shared in the description box, the chat box, and also it will go to your mail. Please fill up the feedback form, because on filling up the feedback form, you will get the certificates. And please fill up the quiz. And now I would like to invite Paramita De to give the vote of thanks. Paramita De, please take over the stage. Thank you.
Respected Chief Guest, Professor Saikat Maitra, Honourable Vice Chancellor of MAKAUT, Revered Principal, Professor Krishnendu Chakrabarty, my dear colleagues, participants, and beloved students, I feel honoured and privileged to propose a vote of thanks to all who helped us in various capacity to make this webinar a grand success. First of all, I'd like to express my heartfelt vote of thanks to our chief guest, Professor Saikat Maitra, Honourable VC of MAKAUT, for gracing the webinar and delivering a keynote address to our participants. Very heartfelt thanks for his interesting talk and thought-provoking address. I'd like to propose a hearty vote of thanks to our distinguished speakers, Professor Amlan Chakrabarti, School of IT, Calcutta University, and Professor Sharbani Roy, Department of Computer Science and Engineering, Dalton University, for their illuminating deliberation on deep learning and participatory and sensing network. I hope that all participants were thrilled by the expedition into its realm of inert manuals and beauties of this topic. I'd also like to thank our young speakers and budding scientists, Agneet of Softcore, Ridajit of ISI, and Chojanno of Q Kolkata, and Shanisha, our MTech student, for their excellent presentation and making this webinar interesting and meaningful. We're confident that the participants would derive due encouragement from these exposures and fill exemplary technical careers in future in these newly emerging fields of deep learning, social networking, IoT, and quantum computing. During the webinar, we have conducted a quiz for every technical session. Due to the huge response of the quiz, we cannot publish the results in such a small tenure, but we'll publish this name in the website and will give you a special certificate as a token of appreciation along with their e-certificate, which will deliver to all participants through their registered email address after submission of feedback form. Our revered principal, chief patron of the webinar, also shown his great enthusiasm for successful completion of such academic achievement, and this time there has been no exception. Without his able guidance all through, nothing could be arranged in such a beautiful manner. Thank you, sir. And I want to thank Dr. Maitra, HOD of IT, Dr. Kalpana Shaharai, HOD of CSE, and for their constant support and participation. I want to specially mention Professor Rituparna Sen, IQAC coordinator of our college, for his guidance and help. He helped in wide circulation of this event in alumni and students of the group. All these three HODs, for their constant participation in the event, I feel really enthusiastic. I'd like to thank Professor Krishnendu for his guidance. From program designing to certificate creation, he was a constant support for us. I'd like to thank Joy Datta, Jodhpur University, for wide circulation of the event. He created a feedback page for the event in Facebook, and there was a huge response from there. And I want to thank all of my colleagues, Ritik, Atanu, Partho, Shama, Pranay, Alok, Shomit, for their constant support and participation. I'd also like to thank Shrupriya Das of Skyline Web and Application for his tireless effort to extend technical support for the last couple of days, which enabled us to run this webinar in such an unhindered way in virtual mode. Now, in my family fund, I want to thank my daughter for her quick support when my presentation share button was not working yesterday, and she arranged it in my mobile as I felt terribly nervous at that time. I want to thank Kinshu for organizing the event with me, and he managed all this situation with such a graceful manner. Finally, the wonderful students, faculties, researchers who have turned up in great numbers, not only from our institute or our country, but all parts of the world. Thank you so much for your cooperation and active participation. Once again, I thank all of you for your cordial support to make this webinar a grand success.
Thank you, Paramita Di. This concludes our two-day webinar. I thank all the participants, the dignitaries and eminent speakers for their participation, and I hope that you will join us again when we arrange another webinar. Thank you very much. This concludes today's webinar. Thank you.
Supriyo.
Hello.
Stop the
Hello.
recording.
Stop recording.
Good afternoon.
Good afternoon. Supriyo, please stop recording. ঠিক আছে।
হ্যাঁ, কিরম হলো ঋতুদা?
ফার্স্ট ক্লাস।
এইবার ঠিক আছে। এইবার ঋতুদা ঠিক আছে।
আপনি তো পুরো
আমি ওই জন্য এখন
লাইটটাও বন্ধ করে দিন।
লাইভ বন্ধ হয়নি?
লাইটটাও দেখে নিচ্ছেন।
লাইভ বন্ধ হয়ে গেছে।
হ্যাঁ হয়ে গেছে।
এখন